and be respectful. We have a code of conduct, and you will find it pinned at the top of the eBPF Summit Slack. If you have any concerns at all today, please get in touch with Beatrice Martinez. You will find Beatrice on Slack.
And just like yesterday, we're going to be collecting questions inside the Slack. You all did such a wonderful job asking questions of our speakers yesterday and keeping that interactivity going. Let's try and keep that going again today. So at keynotes, as we learned yesterday, we'll have a live Q&A session at the end of their presentation, and we'll be asking the questions that you have asked in the Slack or given an emoji to live. On the lightning talks, you'll be able to get your questions answered directly inside of the Slack. We had 4,500 views of our live stream yesterday, which was amazing. I mean, we put a lot of work into this, and so it's really great to see that sort of a reception. We also had some really fun social media posts, things like Liz Rice reminding us of like some of the words of Tabitha Sable and Martinez yesterday, saying, just think backwards and in hexadecimal when trying to figure out how to map an IP address.
Awesome. Let's check out some of the keynotes today. First up, we will hear from Liz Rice from Isovalent. Liz will teach us how to build a load balancer from scratch. Then we'll hear from Daniel Bernier from Bell Canada. Daniel will share his view on why eBPF is changing the telco networking space. And then finally, Daniel Borkman, also Isovalent and co-maintainer of eBPF, will talk about eBPF and Spectre, mitigating transient execution attacks. That will definitely be interesting as well.
And today's sessions, the lightning sessions, will be broken up across 3 different topics: networking, writing eBPF programs, and advanced eBPF for experts. So there's lots of stuff to cover. And I wanted to call out real quickly that if you're watching this stream live, you might want to subscribe to this channel, and that way you'll be notified of any of other events that are coming up, including Echo Office Hours, which we do every week, and Liz and I co-host it.
We got a ton of great feedback from our Capture the Flag run yesterday. So today at 11:05, we will join Taby Sable again, and we'll explore the second stage of the Capture the Flag. Challenge 2 has been published yesterday. It's still available for solving, so if you have not solved it yet, you still have time. We also just published challenge number 3 about 2 hours ago. You will find both challenges in the eBPF Summit Slack channel. Challenge number 3 we will be solving on the Echo live stream tomorrow. If you don't know about Echo yet, Echo is the eBPF and Cilium live stream hosted by Liz and Duffy, so kind of like office hours. Definitely worth checking out if you want to stay up to date with eBPF.
Today, August 19th, is International Photography Day, and a couple of you have already posted some live bee shots that you've taken. We're going to keep the bee artwork going, so if you have a great piece of art or something else with bees in it that you like, definitely post that in the channel. We're all looking forward to seeing more of that.
Great, and we do hope you are enjoying the summit so far, but we also want to continue improving. So please do fill out the feedback survey that gets posted into the Slack channel regularly. Thank you very much.
And now it is my honor to introduce Liz Rice, going to teach us how to write a load balancer from scratch. Thank you very much, and we'll see you soon.
Hi, I'm Liz Rice, and today I'm going to write an eBPF load balancer in a few lines of C code. This is going to be a long way from production ready, but hopefully it will be sufficient to give you an idea how we can use eBPF to manipulate network packets and create network functionality. So a load balancer is going to take HTTP requests from a client and forward them on to one of a set of backends. Now, in my demonstration today, all of my components are running as Docker containers on the same host. And that gives me some advantages in terms of how addresses are assigned. Docker gives each container an IP address. They're all the same except for the last byte. And also, Docker sets up a virtual Ethernet connection for each component. And the MAC address for that Ethernet interface, the last 4 bytes are the same as the IP address. So I know that whenever I'm manipulating an address, both the MAC address and the IP address only vary in their last byte between all my different containers. So I could send a request from the client to one of the backends, and let's just take a look at the kind of response we get. So from backend A, we get this simple response, and backend B responds very similarly, but we can see which server we were talking to. Now I want to be able to send my request to the load balancer, and I'm going to have an eBPF program attached to the express data path, XDP, on the virtual Ethernet interface for the load balancing container. And that program is going to decide what to do with the packet, whether to send it to one backend or the other. So that XDP program, it's being called when a network packet's received, and it's as soon as the network packet arrives at this interface. So it hasn't been through any of the networking stack. And the XDP program can inspect the packet, potentially modify it. And then when it exits, the return code tells the kernel what to do next with the packet. There are a couple of return codes we're interested in. One is pass, which says, pass this packet up the networking stack as you would have done if there wasn't an XDP program here. And TX, which says, take that packet and send it back out through the interface that it came in on. There's one other thing we need to know if we're going to manipulate network packets, and that is how they're structured. So we're using a virtual Ethernet interface, so we know it will start with an Ethernet header. The protocol indicator in that header will tell us whether or not it's an IP packet, and if so, the Ethernet header is followed by an IP header, and that will tell us whether it's a TCP packet or not. We're only interested in TCP packets. The other thing that we need to know about an IP header is that it has a checksum. So if we change anything about that IP header, we're going to also have to update the checksum. And we have some C structures that tell us how the Ethernet header and the IP header are laid out. So let's take a look at some code. So to start with, I've got basically hard coding for my IP addresses. They all start 172.17.0. something, and that last byte I've hard coded here for each of my components. And then here's an outline of the eBPF program that we're going to attach to that interface. And we could just have some tracing to say that we got triggered, we received some kind of packet, and then we'll return the pass return code so that the packet is handled as it would have been if we didn't have an XDP program here. So I'm just going to run make here. My make file compiles that code into a BPF target object file. And then the make file also uses BPF tool to detach any pre-existing XDP programs on that interface, load the object file or load the BPF program and attach it to the ETH0 virtual interface. So now if I make that request to the load balancer's IP address, now that request fails because there's nothing on the load balancer listening on port 80 expecting to handle web traffic. But if we take a look at the tracing, we can see that some tracing got generated. We received some packets. So now we could start looking at the packets that we received. And we get these pointers that tell us where the data starts and ends. We have to be careful not to try to read anything outside of those boundaries, otherwise the verifier will complain. And we know that the packet is going to start with an Ethernet header. We need to make sure that there's enough space in that packet for the Ethernet header. So size of struct header. If that goes beyond data end, then bad things have happened. So we would want to abort. Otherwise, we can look at the protocol indicated by this header, and we are only interested in IP packets. Anything else, we will just pass up the stack. Oops. Now, this hproto field is actually 2 bytes long, and I need to worry about byte ordering. And there is a helper that will do that for me. If you don't know what I mean by this, this is that we don't know whether bytes are ordered on the network in the same order that they are held in memory on this machine. So that helper function will take care of that for us. So at this point, we know we've got an IP packet, and we can look at the IP header in much the same way as we looked at the Ethernet header. So let's change this to IP. It's an IP header. It immediately follows the Ethernet header. And we need to make sure that there's enough room in the packet for the IP header as well as the Ethernet header. And then we can look at the protocol indicator in the IP header, and we are only interested in TCP packets. Anything else, we will pass. Now, this is 1 byte, so we don't need to worry about byte ordering here. I'm going to change this return code to say if we've got a TCP packet, we will use TX. That's going to change the behavior. Let's also just have some tracing here to say we got TCP packet, and we'll put in the address that it came from, which is the source address here. Okay, so let's make that. And let's try making that request to the load balancer again. This time, we don't immediately get a response. If we look at the tracing output, we'll see we've got network packets. We can see they are TCP packets. The address is actually in reverse order. So that 4 is the last byte of the address, the way we ordered it here. So it's a packet coming from the client, as we would expect. And we're just sending that back out through an interface, but there's nowhere for it to go because it's currently addressed to be received by the load balancer. So we need to change that. We need to change the destination address. Let's just pick backend A for now. I've changed the IP header, so I need to update the checksum, and I've got a little function to help with this because it's not super interesting, but if you want to, you can check out the code on GitHub. There's one other thing I need to do here. Because I'm sending that packet straight back out of the network interface, there's no networking stack that's going to check. I need to put IP address here, don't I? Address for backend A. There's nothing to convert this IP address to a MAC address. So the packet, we need to update the destination MAC address in the Ethernet header. Otherwise, the network won't know where to send that packet. So I only actually need to change the last byte of that MAC address, because as we know, they're the same bar the last byte across all the components. All right, let's make this and see what happens. Okay, we're not getting a response back. If we look at the tracing, we see that we've got some packets, and some of them are coming back from the address ending in 2, whereas others are coming from the address ending in 4. And 4 is the client, 2 is backend A. And if we take a look at backend A and we run TCP dump here, And let's just run that request again. So we should start seeing some traffic on from backend A's perspective. And we can see here that backend A is receiving some traffic from let's find a receive. Here we go. So it's receiving traffic from the address ending in 4, and then it's trying to reply to the address ending in 4. And the address ending in 4 is the client. And of course, the client thinks it's talking to the load balancer. So it's not expecting to receive these responses from the backend. We need to change the source address as well as the destination address so that the backend sees this packet as if it were coming from the load balancer. It will be coming from the load balancer. So let's change the source address to the IP address of the load balancer. And we'll also change the source MAC address to match. Okay, let's try making that and see what happens. And we'll make the request again. We should be seeing, we're seeing lots of traffic on the load balancer. We can see we're receiving packets from both the backend and the client. And if we look from the backend's perspective, let's make sure we're looking at the end. So now we can see packets that are arriving from the address ending in 5, which is the load balancer. And now it's responding, it's sending those replies back to the address ending in 5, which is the load balancer. And so those packets are arriving on the virtual Ethernet interface for the load balancer, and they're triggering this program again. We need to send requests from the client onto the backend and responses from the backend back to the client. So one way we can do that is to look at the source address and say, if it came from the client, then we'll forward to the backend. Otherwise, we will forward to the client. So this should be a response. Okay. We make this and see what happens. We issue a new request. We get a response. We're successfully able to send the request from the client via the load balancer to the backend and get the response coming back the other way. So the only thing we need to do now is make this into a load balancer that can randomly pick between 2 backends. So let's say that by default, it's going to pick backend A. We'll change this to be a variable. And we will look at the time in nanoseconds. And we'll basically use whether it's divisible by 2 to choose whether we're using backend A or B. So let's make that. And with a bit of luck, if we start making requests, sometimes the response will come from backend B. Sometimes it will come from backend B twice in a row. Sometimes it will take a moment to respond, which is just making me nervous, but it came back with backend A. And there's another response from backend A, and there's a response from backend B. So we are having the load balancer pick more or less at random between the 2 different backends. We've built a very primitive load balancer. Now, there is a lot to do if we wanted this to be usable. We probably wouldn't want to hard code the address information. We could store that in maps. And then we'd be able to populate that address information from user space. Another thing we would need to do to make this a usable load balancer would be to have the ability to handle multiple clients. We probably want to map client IP and port addresses to different ports on the load balancer so we could correlate requests and responses from different clients. If you want to take a look at the code, you'll find that on my GitHub. And if you want to know more about XDP and load balancing, check out the Echo YouTube episode number 9, where I spoke at some length with Daniel Borkman about XDP and load balancing. I hope that's given you a little insight into how we can use eBPF for networking code. I really hope that you're asking me questions on Slack right now. As I record this, I'm really looking forward to meeting you all online at eBPF Summit.
Thank you for that amazing talk. It was really awesome. It's always amazing to watch people live code, you know.
Thanks.
So we have some
enjoyed
questions
it. I've
for
nice
you.
Comments.
Yeah. One of the first questions that we have for you is multiple questions, but basically it's all the same topic. Is there a performance impact, CPU network latency, due to XDP, since we are intercepting all packets for inspection, even when just passing them up? And how can we measure it? How does this performance impact compare with an equivalent hard-coded IP tables-based load balancer or with hardware load balancers?
So I think the really cool thing about XDP is that you're pulling the packet, or you're able to inspect the packet as close as is possible to it being on the wire. You know, it might be implemented in the kernel, or it might be in the network driver. Some NICs actually even support XDP within the NIC itself. So, you know, you're getting a very, very early look at that packet. So that means, particularly if you are going to turn it around and send it straight back out again, that's really fast. I think in terms of actually measuring the impact, I would recommend going and looking at the blog post that the Cilium team did about measuring networking performance, because there's some really great benchmarks and some really good explanations of the different things that you can measure. Because, you know, you can always, when you're looking at performance, you could always pick some pathological case that's either really, really fast or really, really slow. So you've got to measure lots of different things. Indeed. We should get somebody to post into Slack the link to that blog post. So, yeah.
That would be good. And then somebody asks, what libraries and languages would you recommend for an absolute eBPF beginner to play with for starting out?
Yeah, so when you're writing eBPF code, you have to think about the code that's going to run in the kernel and probably some user space code that's going to interact with it. So for the code that runs in the kernel, up until pretty recently, you kind of had to write that in C, although now if you're a Rustation, the Rust compiler also will compile to a BPF target. So you do have those options. For the user space code, you've got a lot more choices. There's going to be a talk later on today by Kyle Quest, where he's going to give us an overview of the different libraries and frameworks that are out there. I would say pick the language that you're most comfortable with.
Awesome. Our next question is, one day I hope XDP has checksum helper functions outside of BPF csum diff by Emily Wagner.
I completely agree with that. Yes. It's kind of, so there's another hook point at TC where you'd be manipulating packets at kind of more the socket level. And there are some helper functions that will help you manipulate like the headers directly to fix up the checksum directly. But at XDP, you kind of have to do this extra kind of manual work. So it would be great to have some helper functions there, I thought.
We've seen lots of great feedback on this, and I think a number of folks are actually asking, like, do you want to dig into this on like some Echo office hours or some such, because they really love the way you teach. So
yeah,
thank you very much.
We can dig into some of those next steps, because there's definitely, I mean, that
I think it would take a lot of Echo episodes to make it production ready, but there's certainly some more steps we could explore in one of those. So yeah, I'll try and line that up.
Yep. Looks like somebody shared the GitHub repository. Well, thank you, Liz. And now I guess you're going to get a break, and we're going to pass over to Thomas, who will introduce our next keynote speaker.
What an amazing talk from Liz. It's kind of fascinating that eBPF puts us into this position where in 15 minutes we can introduce kind of how to build a load balancer that can then, if you build it out a little bit further, compete with expensive load balancers that are out there. I think it's super fascinating. And we'll continue right off in the networking area. Next up is Daniel Bernier. Daniel has been in the telco space for quite a while, lots of insights, and he will share a little bit with us. Daniel will be talking about why eBPF is changing the telco networking space. Please give Daniel a warm welcome.
Hello, my name is Daniel Bernier. I'm a technical director in Bell Canada, and today I'm going to talk about why is eBPF changing the telco networking space. The changing landscape of ISP networks. So right now, the industry is seeing a big transformation around how telecom operators or ISPs are evolving and the services they're offering are changing. First of all, cloud transformation. You already see in the news and blog posts how 5G is pushing towards a cloud-native approach to end a growing erosion towards hyperscaler clouds of some of the new network functions or the new services coming with 5G. We also know that a massive scale requirement will be there for operators to support IoT devices, new phones, new cell towers, and the infrastructure and the applications that follow it. Changing completely the way we normally think about how to offer services and the security posture and other capabilities we have over the network. We see a move towards decentralization and edge computing and personalization of the internet footprint with localized apps, low latency requirements, and fine-grained application policies up to the application in the tablets in a home. We do see a commoditization. Internet is now becoming an essential service. Hello, can you hear me? Hello, my name is Daniel Bernier. I'm a technical director in Bell Canada, and today I'm going to talk about why is eBPF changing the telco networking space. The changing landscape of ISP networks. So right now, the industry is seeing a big transformation around how telecom operators or ISPs are evolving and the services they're offering are changing. First of all, cloud transformation. You already see in the news and blog posts how 5G is pushing towards a cloud-native approach to end a growing erosion towards hyperscaler clouds of some of the new network functions or the new services coming with 5G. We also know that a massive scale requirement will be there for operators to support IoT devices, new phones, new cell towers, and the infrastructure and the applications that follow it. Changing completely the way we normally think about how to offer services and the security posture and other capabilities we have over the network. We see a move towards decentralization and edge computing and personalization of the internet footprint with localized apps, low latency requirements, and fine-grained application policies up to the application in the tablets in a home. We do see a commoditization. Internet is now becoming an essential service in most regions of the world. And you see how this is changing the way an operator is able to charge services or offer the revenues associated to it. We also see the value-add services are now moving to OTT space, which was normally not the footprint of an operator. So how can an operator make its network essential and optimize to the growing needs towards OTT applications and third-party developer ecosystem? But we still see an increased pressure or even a greater pressure towards quality of experience for end users. We are now being measured against speed, latency, MOS for gaming, cloud access, TV delivery, and the list goes on and on and on. So we do see there needs to be something happening to evolve the way our network works with those applications. So much that when the ITUT worked on their focus group towards what would the network of 2030 look like, one of the big learnings was there was a failure in how can the applications and the services are tied to the network in a way that was seamless and more efficient. At the same time, we see a growing requirements that can we get the network out of the way? How can we make our network less complex to the developers and the applications, and not necessarily requiring large networking engineers to understand how can this be tied together? Some of the answers come from protocols. So the ITF, in their answer, are looking at application-aware networking and path-aware networking research groups to find a way to make that linkage between the operator network or the network and the application itself. The trouble is that it's looking at the network device, the network operator systems to be the network equipments to be that edge. While in reality, if you look at this, where is the real edge between an application and the network? It resides at the host, at the kernel level, or sometimes at the user space level. And this is where, in my mind, an APN edge would be something mostly connected to an eBPF program or some kind of hooks that an application can leverage. And then you have a real integrated system and no need for intermediate protocol or header exchanges and things like this. What we have also seen through the industry is what other disruptions have shown us. For example, P4 came in, and with it came the democratization of ASICs programming, and proved that end users, operators, or vendors could rapidly create, test, try new concepts, not even standardized, in up to raw ASIC capabilities with increasing speeds. It also showed the benefits of a strong open community, emerging industry academia, generating various new ideas and concepts that can leverage hardware and data plane, from machine learning algorithms running on switches to load balancing running at high speed in a commodity hardware. We also saw the rapid implementation and testing of even reference standards not fully baked. For example, in our case, when we worked with Barefoot and the segment routing architecture group, how could we implement quickly a new draft at its infancy in ASIC, even if it took 4 years later on to get officially ratified. And the code was able to evolve even for hardware at the speed as the draft were evolving, proving the flexibility. So ideally, we'd like to be able to have the same capabilities in a Linux host. Can we prototype, create specific functions which are not necessarily made to be fully included into the Linux kernel, for example, or can we rapidly evolve and integrate new capabilities in a host using programmability? So it comes to how can eBPF be developed in the telco networks or being used in the telco networks. One good example is in-band telemetry. So we know how to do observability in eBPF from a host level. What the Intel folks did is actually, rather than use a P4 code on FPGAs or SmartNICs or an ASIC, they actually extended that capability to the host using the P4, using eBPF. So you are now able to encode without having to change anything on the Linux kernel, use for in-band telemetry, the int header, and be able to encode the data you want as it traverses the network, including the capability to integrate with physical devices supporting the int headers formats. Another example is the eBPF work that was done by University of in Belgium. What they did is they created a function that could reside in eBPF so that people could be able to create their own functions leveraging the segment routing network programming logic, which in case means that anybody can create a network function or a behavior in a host and code it so that it's tied to an IPv6 address and then publicly reachable. Of course, if it was to be done in the mainstream Linux kernel, means everybody wanting to create a new function, even if it's for its own use only, would have to go in and make it merge into the kernel for the networking piece. What happened instead is with the end.bpf, you leverage the seg6 local capabilities, which were already added to the kernel, and you hook it up to the end.bpf function where you can actually create those independently without having to necessarily circle back to the kernel development cycle. And you add this using the IP route logic, including the segment 6 instructions, and how you can do this. Another, which is something dear to my heart, is how can we augment Kubernetes networking for telcos? So as we move product applications from standard virtual machines and things like this to the Kubernetes engines and clouds, the Kubernetes structure was not built for the way operators and network functions were built, with multiple interfaces, different parameters, VRF support. So the initial model was to leverage things like multiple interfaces and meta CNIs to create that abstraction through independent interfaces. But still, it doesn't tie back to the rest of an operator network. So we translate into VLANs and some other basic plumbing, but in the end, an operator network doesn't work like this. So what if we could leverage eBPF capabilities to create those encapsulations that make sense and hook it up to the rest of the operator control plane, so that actually I could have VRF segmentations and logics within a Kubernetes cluster without having necessarily to have multiple CNIs and multiple interfaces and creating those kind of complexities. And at the same time, still leverage the great work done on observability and the security features that can be added through eBPF, which is something not trivial if you do it only from the network, like the layer 7 policies and those kind of things. At the same time, you can look at how can we rethink the network functions with eBPF. So from the industry perspective, and this is no news, we haven't done really major rethinking of a network function. What we did is we changed the packaging. So we came from physical devices with everything proprietary and all those things, we know the story, to virtual network functions, but in essence was almost the same difference, just a different package. We could not modify this that easily. And you go to containers, and in the case of containers, we still haven't changed the way the application is built. We need an out-of-band net interface. We need a different interface for OEM. We need a different interface for data plane. We need some other hooks to be able to control it, like if it was a network function, and not really leveraging the cloud capabilities or the cloud learnings. So what if, instead of doing, and the way the industry is doing right now, is try to push everything to user space, because people are afraid of going to the kernel to either for latency purposes or flexibility purposes. So you push everything to user space, and then every time you need to tie an application to it, you either go back to standard mechanisms, or you need to recreate your own TCP stack, for example, which is something happening in user space land right now. What if instead those functions were microprograms running in eBPF, running at the eBPF layer, and the applications would leverage them as they go through the network, and you would just need to have the proper libraries and SDKs to create and hook those functions together to create a microprograms. In that case, complexity of user space versus kernel space and then network space would completely be eroded, and we could be able to leverage a single structure, also limiting the complexity. So if you look at this, you look at the UCP use case. For those who don't know what a UCP is, it's a small device you send to a customer premise where you do virtualized network functions. Right now, what we do is we ship a box, high cost, lots of CPU cores to be able to run virtual machines in there, to sometimes do simple things as NAT, or a bit of DDoS at limited rate, or other kind of simplified complex applications. The next evolution would be, can I do the same thing but using containers? And in that case, you do MEMIF interface or other user space mechanism to try and hook those functions together, or you use libvirt and SRIOV at the switch level to do those at the same speeds. You still have the complexity. You're just recreating the thing in a different package, because you're expecting that container network functions will be simpler to operate than a virtual machine. In reality, we could say, well, those microprograms, NAT, DDoS, small other footprints, DPI, or observability packet capture could be done as microprogram in eBPF. And the only thing you need to understand is the logic to hook those together. In that case, a footprint of a UCP would be largely diminished, going from a multi-core high-scale processor to small IoT device gateways being able to do those simple functions when they need to and where they need to. Example of this, it's actually in reality. Some people worked in the community, open source, on how to create a full-blown 5G UPF using BPF. And if you look at this from small functions like IoT gateways requiring local breakout for some sensors analytics, why would we need a complex, large scale, big vendor UPF? Could we leverage something small like this because the throughput is limited? Those kind of things, and even then with eBPF, the throughput would be quite good and quite in good numbers. So in that case, you really see that those BPF functions, if you look correctly, you can actually create new network functions, leveraging this mechanism and hook them to your network. Again, simplifying the way we would actually abstract and orchestrate those functions. And if you look into the future, if I'm able to create my functions and leverage the Linux underlying eBPF structure across my various flavors of Linux, from automotive grade Linux to the Kubernetes, or even some kind of the Android if available, then you realize that some small programs you need to do that you normally aggregate into larger data centers in more complex systems could run at small scale, small footprint, ease of management through as in a residential gateway, a connected car, or any kind of other environment. And in that case, you would still be able to leverage the fine-grained visibility security capabilities, increase or augment the networking requirements as you need to, and increase the high-speed data plane of choice by using Linux eBPF rather than having to do some other capabilities, either through SROV, which cannot run on those kind of environments, and you can also not run user space functions like with DPDK as you wish in those kind of environments. Again, a good use case or good view of how could eBPF evolve and transform the way the networking space is done in telecommunication networks. With that, I give you thank you and hope that you will have some interesting questions for me. Have a good day.
What an amazing talk, Daniel. Thanks a lot. So please give a round of applause, a virtual applause to Daniel, and let's see what type of questions we got in. The first question we have is from Paul. You argued the edge should be the hosts where eBPF can run. Do you think having this programmability at the edge will decrease the need for hardware programmability, such as P4, Tofino, etc., in the network itself?
I believe not. We've proven through P4 and the ecosystem it kind of generated, programmability of hardware is still required, actually even more required than we thought before. I think it's really a question of where to position those instructions in the code when it makes sense. So if it's really bound to an application at the source, try to make it as close as possible, but sometimes that programmability needs to be in ordered, like in different devices. And in that case, P4 or equivalent languages for other ISIC would still be required. It's just a matter of placement.
Excellent. The second question, how can telco move away from multiple interfaces for network functions using eBPF? Can you please elaborate on that? Thank you.
Yeah, the question is more around how can we abstract that segmentation, which is sometimes required. So most of the time, it is either a segmentation of route lookups that can be done differently with source routing paradigm like we do in segment routing, for example, and sometimes it's an isolation of performance. So of course, if there's still cases for SIOV interfaces, that kind of abstraction would be there. But sometimes having a system need to talk to two different routing domains doesn't necessarily mean it needs to be segmented to different virtual interfaces. I think it was just done so that we leverage the tooling that was at the moment and not look at how can we make that tooling different.
Excellent. And then for the third question, we have, do you see VNF vendors starting to use eBPF programs instead of SRRV and user space libraries? Do you expect Bell Canada or other ISPs will have to develop those programs themselves?
I think it's a different, it depends on what. So you're going to see specific functions. You do see VNF vendors starting to involve, do more efforts around BPF programming for their functions rather than leverage SROV or DPDK specifically, like the standard model. So you do see that for data plane development. And there's cases where I think we are operators like Bell Canada, or through the ecosystem we have with our kernel suppliers, we will start to see those kind of small programs being injected directly within the the network OSs we use, like some DDoS capabilities, some packet capture capabilities. I think this will become as an ecosystem pre-built into some of our systems, and we just hook them up and deploy them.
Great. And then one question that I really found interesting, what can library maintainers do to help make things easier for telcos in making eBPF network function, data planes, and user space components?
I think it's a great question. I would say it's the same question that the P4 community is trying to figure out, is how can we make those kind of data plane programming, either from an SDK level, simplifying the way anybody can code, can start coding some simple functions, because we're not all as Liz Rice and do it live coding. So how can we make those things happen? And how can we normalize the way we do those system calls or hooks to the eBPF program so that it doesn't become a one-to-one mapping across every program? I'm going to give you the example of P4 because I came to eBPF later than P4, but P4 runtime was about how to make those things kind of more linear around an ASIC programming, the P4 language. I would hope that we start to see the same for eBPF programs.
Yeah, and I think the eBPF Foundation can play a role here to help facilitate this learning and get the resources together. So thanks a lot, Daniel. This was a great talk. Thanks for all of your insights. Please give another round of applause to Daniel. And we'll be taking a quick break. So we will see each other again in about 5 minutes with the next set of talks. See you in 5 minutes.
Welcome back. And now we're transitioning to one of my favorite topics, networking. There's going to be a ton of really great talks here. We're going to have a break in the middle, but we have quite a number of really great networking talks to present. The first will be Karthikeyan Thangaraj from Verizon Media talking about software L4 load balancing for Kubernetes services at Yahoo.
Hello everyone, thanks for joining me in the talk. Today we are going to talk about software L4 load balancing for Kubernetes service at Yahoo. I'm Karthikeyan Thangaraj. I'm a production engineer at Yahoo, focusing on modernizing Yahoo tech stack in a cloud-native way. Let's get started by taking a look at Kubernetes scale at Yahoo. Overall, we have 2,400 plus applications in 34 production clusters across 7 data centers. Our Ingress stack handles 2 million peak RPS. This is the screenshot from our Prometheus preparation showing the number of nodes and pods and applications that we run across the board. We wanted to solve the traditional hardware load balancer problem where the servers are pre-configured with the hardware load balancer, and any changes to the servers need a configuration push. LB APIs are not optimized for the dynamic updates, so automatically adding servers in a web is not possible. Of course, auto scaling is not possible. If you want to scale a service behind a web, we need to add the service manually. Another problem we wanted to solve is performance degradation with large number of test services. As we all know that kubeproxy is IP table based, it generates long list of IP tables rules. Packet has to enumerate through long list of IP table rules to locate service in the pods. This introduces performance degradation. This is a very nice blog post shows how the performance got degraded while accessing the first services to the last services in a cluster of 50,000 services. Why we choose Cilium as a software L4 LB? Commodity hardware can be deployed as a software L4 LB. With this, scaling the LB is as simple as adding the service. With XTP, performance is at par with hardware LB, so there is no compromise on the performance. As Cilium is hooked directly into the K8s API, any changes to the backend part gets updated to the L4 LB instantaneously. Cilium L4 LB makes the same decision across the board, so any packet part of a connection can be routed to any LB. It also supports DSR mode, which makes us no difference with the hardware LB. With Maglo consistent hashing, Cilium makes a highly available and reliable software load balancer. Let me walk you through how the traffic gets routed to the application pod through Cilium LB with an example. Let's say we have an application deployment with 3 replicas and a service with an external IP 2.2.2.2. This IP is a WIP IP, and in our case, it's an Anycast IP as well. And with Anycast IP, many Cilium LB nodes are responsible for it. And traffic to the many Cilium LB nodes are load balanced through ECMP. When a client sends a request to 2.2.2.2, the request lands on one of the Cilium LB nodes. As the Cilium LB nodes are directly hooked to the Kubernetes API, it knows about the backend pods, where to route. With Maglo consistent hashing, it picks a pod and then forwards the packet to the pod. And the Cilium agent on the node where the pod is running helps to redirect the traffic back to the client. In our setup, we run Bird as a daemon. Bird helps in advertising the routes of the web to the network. And also it helps to establish a BFT session with the tar. BFT is bidirectional forward detection. This helps to detect the network failure in the forwarding path. BFT works by exchanging the control packets between the two network devices. When there is a timeout between the control packets, then that particular path is considered as a failure. In our setup, we have configured 15 milliseconds for the one control packet exchange, and we have set 3 retries. So with the 150 milliseconds, a particular node and the network is failed, it can able to detect it and then can able to take it out of production automatically. If the BFT session is broken in the tar considers the network path for the LB node is failing, and the tar helps in announcing the new routes to the network, and then the network will not route the traffic to this L4 LB node. Hence, it is taken out of production automatically. So in our setup, a particular LB node on a failure case can able to go out of rotation automatically in 150 milliseconds. Okay. This diagram represents our data center network topology. You see in the picture, server in the rack connected to the tar, and the tars are connected to the leaf, and leaf is connected to the spine. So we run spine leaf architecture in the data center, and all the devices are enabled with ECMP. ECMP helps to load balance the incoming traffic across multiple load balancer nodes. Traffic from the internet enters through the Yahoo data center to the spine, and the spine can able to do an ECMP and send the traffic to the L4 LB node. And the L4 LB node with XTB can able to redirect the packets to the corresponding pod, and the pod gives the response back to the client directly in the request served. to the client. We did an extensive performance test to make sure that traffic routed through the Cilium LB doesn't have a performance overhead. We did a number of tests, and one of the sample test results is shown in the table. We observed only a small latency overhead in microseconds when traffic is routed through the Cilium LB, and this is in par with hardware load balancer. And we are just starting with Cilium, and we are deployed across 2 data centers, and 1 production application is routed through the described solution. And we are expediting to move every workload to the Cilium LB solution in Q3, Q4. And with this, I'm concluding. Thank you so much for listening to the talk. Please post your questions in the Slack. Thank you.
Thank you, Karthikeyan, for that view into how this is working at Yahoo. Remember, if you have any questions or any feedback for Karthikeyan, you can put that right into the Slack, and we can get those answered for you. Our next talk will be by Nick from DigitalOcean, who will be talking about rate limiting access to internal services in a virtual network.
Hi everyone, my name is Nick Bugliani. Today I'm going to talk about rate limiting access to internal services in a virtual network. The first thing we will see is the layout of our virtual network. I will then speak about an eBPF XDP rate limiter, and then show you the toolchain we use to build, test, and deploy our eBPF programs. In bonus, I added code sample that you can use to inspire yourself. But first, DigitalOcean. We're a cloud hosting company hosting more than 1 million virtual machines over 13 data centers. On each of these hypervisors, we are using Open vSwitch as a building block to build our virtual network. Let's see how it works. We have an Open vSwitch bridge, and all the virtual machines tab interface are plugged into this bridge. Our physical interfaces are also plugged into this bridge. But what is interesting is that our internal services are accessible through network interfaces that are also plugged into the switch. For example, when an HTTP request that wants to reach the metadata service comes from a virtual machine, it will go through the Meta0 interface. Well, as you can imagine, we don't want to have too many packets reaching these services. It's possible to rate limit at the application layer, but in our case, we decided we want to rate limit earlier to make sure that the workload on these services is as low as possible. That's where we decided to use an XDP rate limiter that we attach to these interfaces, like Meta0. Let's see the rate limiter. We have the code here. The first thing that we see is that we're using a hash map to store a MAC address per MAC address state. So where we store some counters, a timestamp, and the number of packets that is allowed to go through. Here you can see we have the rate limit hard-coded. So there is 100 packets per interval of 5 seconds that are allowed. Well, it's not 100% true, but for our example, that will be true. We're using a token bucket algorithm, which means that when we see the first packet, we initialize a new timestamp. And for all the other packets that we see, we decrease the number of packets that is allowed to go through. When the number of packets allowed to go through reach 0, we check if we are inside this 5-second interval. If we are, we draw the packet. If we're outside this interval, we just initialize a new timestamp and we refill the number of packets that is allowed to go through. We also update statistic, which is awesome because we can extract them and then we can see what is going on per virtual machine. Now let's see the toolchain. We have a makefile here, and this makefile is used to generate the bytecode object using CLang and eBPF. It's also calling Go code that is used to test the program logic and load the object using the Cilium eBPF library. We also attach the XDP program to the network interface using Netlink. We do all this before deploying to make sure that everything is fine with our application. And this toolchain is a Docker-based environment with a fixed version of eBPF. And you can see here that the entry point of this Docker file will kickstart the makefile we just saw. And now let's see the Go code using the Cilium eBPF. The first thing we do is we call load collection spec, which will parse the ELF object. We then call new collection that will load the program and the maps in memory, which also call the verifier to make sure that your program is safe. So we finish by attaching the program to a network interface using a Netlink library. And still, using the Cilium eBPF library, you can test and benchmark your application. Here you can see that we are calling benchmark with a packet we crafted and the number of times we want to send this packet. Using table-driven tests, here we are passing the number of packets we want to send and the outcome we expect. Using this function, you can build very awesome unit tests for your program. And for deploying, it's very simple in our case. We have a bash script that uploads the program object file to an artifact server. This file can be accessed through the git hash or the timestamp. This allows Chef to pull the object file, and using the single call we just saw, we put things in place. And in conclusion, we saw our virtual network and how we use the eBPF XDP rate limiter. We also saw the toolchain that we use to build, test the logic, load, verify, and deploy our eBPF application. We saw the awesome Cilium eBPF library, and now you're ready to build your first eBPF program. Thank you.
Thank you, Nick. That was an amazing talk. And now the next one we have is Bad Middlebox Catching RFC 6437 Violations in the Wild by Mark and Lorenz from Cloudflare.
Hi, my name is Mark. My colleague Lorenz and I both work at Cloudflare, working on the Unimog layer 4 load balancer on our edge. Today I'll be talking to you about bad middle boxes, specifically ones that violate the assertions in RFC 6437. Now, violations of RFC 6437 doesn't really have any meaning to it, but in order to explain it, I have to first explain IPv6 flow labels. IPv6 flow labels are a 20-bit field in the IPv6 headers that are meant to contain a client-side value that is consistent for every packet of a connection generated by the client. This field can be used as an alternative to layer 4 headers, such as ports, in hashing algorithms used in load balancers. And the reason that this would be helpful is that on IPv6, finding the layer 4 header and therefore the port fields can be a little bit tricky. And coincidentally, me and Lorenz both work on the load balancer at Cloudflare, and that's also written in eBPF XDP. So being able to see if we can use flow labels instead of ports for IPv6 is quite important. But can we actually use flow labels? Well, there's a blog post from AppNick that says we probably can't. It says that it's probably not a good idea to use it as an input for flow hashing because there are apparently middle boxes on the internet that interfere with this flow label. They suggest that flow label contents between a SYN packet and a subsequent ACK packet that's sent by a client may actually differ. And they surmise that it's probably CPE, so customer routers and equipment, or other middle boxes on the internet that are actually altering this field. But there's not a lot of evidence or numbers in the blog post, so it will be great for us to find out for ourselves if that's really true and how much it occurs on the internet. But how can we actually find this out? Well, enter eBPF. We can use eBPF to determine whether this occurs on our edge. Using the Cilium Cloudflare co-maintained library that's written for Golang, we can do this. The library has BPF2Go, which is a code generator that allows you to have a BPF-C file, and it generates all the bindings for Golang. It has supports for loading and attaching K-probes and support for BPF compile ones run everywhere. Using this library, we will write a BPF K-probe specifically meant for one of the TCP functions in the kernel and load it and attach it. And using perf events, we can actually get that data out from the kernel and into user space so that we can do something with it. But how do we actually make sure that we can see the SYN packet and then the ACK packet and see if the flow labels have changed or not? Well, what we need to do is find a way to record that SYN packet. And the easiest way of doing that is actually a socket option on Linux, where you can instruct the kernel to save the SYN packet for every connection made. Now, this is enabled by default, and enabling it for all our sockets on our edge is a little bit tricky. So here comes the pidfd getfd syscall, where we can actually get the kernel, once we give it a process ID, to enumerate all the file descriptors of that process. And once we have all of those, figure out which ones are TCP ones and which ones are listening sockets. And then actually set the socket option on that socket so that the kernel from that point forwards will save the SYN packet for every established connection. Using this, we can then have our kprobe compare the values, and if the values differ between the flow label in the SYN packet and the flow label in an ACK packet, we can actually generate a report and send that over the perf event buffer into user space and do something with it in user space. And what does that result in? Well, a single Golang compiled binary that's static. It can run mostly anywhere. You don't need to ship any kind of tool chains to our edge machines. You simply give the program a process ID and it finds a TCP socket, sets the socket options, loads the kprobe and attaches it. And if there is indeed middle boxes interfering with packets, we will receive data from the kernel into user space and are able to do something with that. So what we'll do is we have the code that is a proof of concept on GitHub. We'll try and deploy a variant of this code on our edge and come up with some good findings. And once we do have that, we'll try and write up a blog post and share that with everyone. Thanks for listening.
Awesome. Thank you very much, Mark and Lorenz. Let's give a shout out to all of our speakers. And if you have questions for Mark or Lorenz, you can ask them inside the Slack. Our next talk will be a firewall flow sniffer and eBPF by Rafael David Tinoco from Aqua Security.
Hello, my name is Rafael, and today I'll be talking about a tool I developed to understand firewall rules and how eBPF helped solving some of the problems I had. So the initial idea was to identify all the flows happening to and from on hypervisor and all the firewall rules that have acted on those flows. The needs were to run in older kernels in version 4. something and to have the least performance impact as possible. Some of the extra needs were to understand which command originated the flow that was being observed and to see if IPsec has changed or not. So the initial idea was to use contract tools and analyze through shell scripts its outcome, its output, and to sort the output by protocol, source, and destination addresses and ports, and to identify each of those flows and add a trace rule to each, and to check through which of the chains that that flow has passed. The problem with that, it was very hard and it wasn't reliable. Keeping all the trace rules in IP tables can be a nightmare, and it needed a timer for management and for less impact. And we couldn't get incoming flows for closed ports as well. And so I went through which of the existing tools could be used, and I saw that there was a project called ulogd. I tried to use it, but it didn't solve the problem very well because it did not trace each of the discovered flows, and I went for the libraries and programming. So I read libmnl and libnfnetlink libraries to see if I could solve the problem by using them. And what I came up with was basically an event-based glib loop that listened for netfilter contract events, and from all the tracing events being observed by nflog, and it created all the flows in an in-memory structure, sorting them and starting a trace to each of the observed flows. And this trace was responsible for telling me through which of the chains and rules that trace has flow has passed through. This worked very well, but had some problems. So the issues I still had to solve was to, for example, to see which command was responsible for the flow, and also the incoming flows for closed ports. That didn't work because of that. I added a trace it all rule option in ConeTracker, but it was very expensive. So I started doing some eBPF research to see how it could help these problems, and I came up with this project called Portable BPF. which was basically an attempt to create a portable eBPF code that could be part of Contractor, right? And there were three major problems discovered when I was doing that. The first one was older kernels needed a kernel version attribute whenever you were loading BPF inside the kernel. The second one was there was no legacy kprobe perf events interface in libbpf, the library I'm using. And the third one, the old kernels did not have the BTF support, which is something needed for relocations to happen before the eBPF program is loaded in the kernel. So the first one was solved by one of commit of mine to libbpf, introducing a way to set the attribute for the eBPF program with the kernel version, so the kernel would not would allow this program to be loaded. This is particularly for the kernel 4.15. After that kernel, this is not needed anymore. The second one was to create a legacy kprobe event. I saw Andrew had already some proposals, and there was some discussion back and forth upstream. There is currently a proposal upstream with a legacy kprobe event support, which will likely be accepted sooner or later. And then the third problem was to have an external file that with the BTF information needed for all the relocations to happen for the eBPF program to be loaded. And if I can point you to some other repository, I would point you to the BTF hub and all the information about what BTF and how external BTF can be used for older kernels is available there. So it's a very nice reading, but not part of this topic right now. So with the eBPF features and the portable BPF I brought to Contractor, I brought some kprobes being done to specific kernel parts. Those kprobes, the functions are on the top, and I was able to get more information and to add some information from other parts of the kernel instead of only observing the contract information that was being given to me from the netlink communication coming from this from the kernel. With that said, if you remember the initial code with those two event loops happening, what happened was I added a third event loop coming from the eBPF kprobes. And those kprobes would be also adding flows to the in-memory structures I had. And not only that, they would have information of the task that either generated or received the flow. So I could get, for example, comment out of the flow, the task info and the task struct and all that. And how to use the Contractor is very simple. This slide shows you all the options you have, and basically what you do is you execute Contractor with the options, and it shows you all the flows, the destination, the source and destination address and ports. And then with the eBPF part, with the eBPF option, you will also see the command, the PID, and the user that originated that flow. And with the tracing option, you will see all the tables and chains through where the flow has passed through. And that's it. I hope you have liked. And before we close this, I can show you a little bit of Contractor working. So here I have a Bionic machine running on a 4.15 kernel, and I can run Contractor. And if I'm running Contractor, it already loads the BPF program in the kernel for the 4.15 kernel. And I can, for example, access this host and run something, and whenever I stop it, it will tell me that there was a flow happening from the source to the destination in specific IP, where was the command and the user through each of the rules it has passed, and also some of the other packets that happened for name resolution that it caught, and you can see also some of the other random network traffic that has happened for this virtual machine. And the same code can also run, for example, in a 5.8 kernel, where I can do also execute it and then do the same, for example. And then I can see, for example, I'll also ping to generate some ICMP. And you will see that we can see the ICMP flows, the UDP flows, and some of the TCP flows from port 80. So that's it. I hope you like it. Visit the repos, give it a try, send me emails if needed. Thank you.
Wow, that was an amazing presentation. And the GitHub repository has a lot of great detail into how to play with this stuff. I mean, anybody who has chased a problem through IP tables has definitely looked for a tool like this, or has had to try and figure out, like, what is actually happening in packet mangling, which can be hard to trace. So great work. The next presentation we have is using user space tracing to solve DNS problems, because it's always DNS. This will be presented by Andreas Gabrauskas from Palantir.
Hello, everyone. So today we will be talking about using user space tracing to solve DNS problems. I'm Andres, and I've been at Palantir for almost 2 years. Most of my time has been spent inside the production infrastructure group with focus on maintaining our Kubernetes offering. At Palantir, we're passionate about building software that solves problems. We partner with the most important institutions in the world to transform how they use data and technology. Our software has been used to stop terrorist attacks, discover new medicines, and get an edge in the global financial markets, and more. For the past 3 years, Palantir's Kubernetes clusters have been suffering from sporadic DNS failures. Past investigations showed that the packets were getting lost before leaving the host. We were somewhat confident that on-host UDP was at fault. However, none of our metrics captured these low-level failures. We theorized some fixes, but we didn't have a way to make sure the fixes were actually effective. We needed to get signal on these failures. The solution was adding client-level DNS metric. Now that the problem statement is somewhat clear, let us jump into the implementation. I will aim to give you a high-level overview on what it takes to attach a uprobe to every single container in your fleet. BPF potentially gives us multiple avenues to capture DNS traffic. The first option we looked at is monitoring packets directly. We quickly rejected the solution as it was too complex, and it also had unknown performance implications. However, it would have had some technical wins over the solution we ended up going with. Namely, it would have captured 100% of the DNS traffic, and it operates at a level below containers, which avoids some problems we'll discuss in the next slide. The solution we ended up going with are uprobes and attaching uprobes to the libc library. 90% of our user traffic are either Java or Python clients, and they use libc for DNS resolution. These clients are managed by many different teams. BPF gives us a single point to monitor all of them at the same time. We do this by attaching a uprobe to the get address info function. This gives us an accurate representation of our DNS system. Using uprobes also meant we can use the Cilium eBPF library to abstract away a lot of low-level details. The Cilium library gave us primitives to manage individual BPF programs. The next step is scaling it up and managing BPF programs for every container on a host. This comes with two main challenges. The first one is containers are ephemeral. They can come and go as they please. We solve this by having an event-based controller that reacts to events generated by containerd. The second problem, containers ship with their own libraries. This means the on-host libraries are irrelevant. We need to find the actual libraries being used. We do this via the process file system. All we need to do is extract the PID from the same containerd events as previously mentioned and access it via the prod PID route, which we mount on our management container. On the right, you can see the whole control loop. It all starts with containerd emitting some create or delete events. We consume those events, extract the PID, check if the container has the libraries we are looking for, and delegate the Cilium eBPF to either attach or detach the BPF programs. The BPF programs then intercept every DNS call and send the data back to our Go program. where we aggregate the data and send it upstream. This gives us a Go program which can monitor DNS traffic for a single host. The last step is deploying it fleet-wide. Our solution leverages an existing daemon set that we call Rubik's Node Agent. We use it for various host-level tasks. We only had to make minor changes to the daemon set's manifest. On the left, you can see the volumes we had to attach. On the right, you can see the Linux capabilities we needed. Wrapping everything up, we massively improved our DNS observability. We added 2 metrics: an accurate success failure count metric, which captures all the low-level failures we were missing, and a per host P99 response time metric. We also gained team-level knowledge about BPF for future projects. And importantly, we now have a uprobe framework, which we can extend to monitor any binary on any container. Now that we have signal on the original DNS failures, we can run some experiments. On the right, you can see how our DNS queries travel through the stack. As soon as they leave the host, we bump them to TCP. However, while on the host, they're free to use UDP. We theorize that UDP is causing a lot of DNS failures. We can easily test this by switching to DNS over TCP with some pod level manifest changes. The experiment was a great success. Enabling DNS over TCP, we saw a 90% reduction in DNS failures across the fleet. Here you can see one of our larger stacks. DNS failures before the experiment were hovering around 1.3K per hour. After the experiment, they fell to 130 failures per hour. The new metrics gave us confidence our changes are beneficial. Without it, we would have never known that enabling DNS over TCP had such a significant impact to our DNS subsystem. Thank you for listening.
Oh, that's a great presentation. I really like the approach in that one, like being able to measure and then be able to experiment and work through the process until you come up with a reasonable solution. That's a great talk. The next talk we have is by Tony Liu from Alibaba Cloud, who'll be talking about track and analyze TCP retransmission with eBPF.
Hello, everyone. I'm Tony Liu from Alibaba Cloud. Today, we're talking about how to use eBPF to track TCP transmissions. As we all know, TCP gives a reliable, orderly, and error-checked delivery. When there is a packet lost, TCP gets a packet through retransmission. When transmission occurs, it may bring higher latency to applications, especially for latency sensitive, such as Redis. In addition, retransmission may also cause the window smaller and lower throughput, as RPC timeout for even RPC disconnection. In general, the retransmission is an important negative indicator used to indicate the quality of TCP, because retransmission can be easily obtained, and the retransmission indicator is negative, passive, and slow pass indicator. However, only focus on retransmission is limited in the real environment. For example, as shown in the picture on the left, we use TCP DAG to get the details. We can know the details, but performance overhead is massive. If it is counter-exported by the clock file system, such as NetState, you will find the retransmission are divided into many types, but only the entire net namespace. The last picture is the retransmission of a common monitor system. However, to brief retransmission data will introduce a lot of noisy. We also found out that not all retransmission we need to be care. Retransmission need to be classified at least from transmission type, process, and connections. For example, for transmission types, we know that the ITO is the most original and the last method to recover lost packet. However, the TCP stack introduced the TRP early retrans and fast retrans to avoid retransmission for back to ITO. The above avoid impact on the application. Only ITO transmission will cause the minimal latency of 200 milliseconds. Secondly, different program may be running on machine, and we usually don't care about the processes, such as SSH. Finally, transmission is more likely to occur in the internet. Sometimes the internet is not sensitive to latency. Of course, overhead is also important. There is also need to provide easy to integrated interface for monitor system. In summary, we decided to use the eBPF to develop our transmission track analysis tools. We first use the BCC GP Transtore Pi. Currently, only support the TLP type, and it does not meet our needs. At the same time, as the diagnostic tools, BCC is not suitable for long-lived environment. We decided to use eBPF to develop called eBPF. Through key props, we can use the eBPF to collect the transmission event and at the same time maintain the connection track table. Events are passed to the user space through perforing buff and the BPF map, and the user space is passed through the daemon program by Golang to perform a user-defined filter. Then, obtain the transformations with the format specified by the users. It is passed to other monitor system. At the same time, it is very important that this kernel provides the BTF features to support the BPF CUI. However, in our production environment, there are still many kernels that do not support the BTF feature. Therefore, we are based on two solutions to support the BTF. Both are used in our environment. And the next is an example of our eBPF. On the left is the YAML configuration file of eBPF. Each collection will be defined as a job. The filter can be provided in the job field, and the aggregation events is also supported. The output result is shown on the right with JSON format. Next is the eBPF data, which collects through the monitor system, and data is reduced by 5 times with the RTO data. And the next, the data in the picture above it from the PMesh. At the time shown in the bar figure, there was a problem on the where, and the PMesh tools can detect the problem, and the eBPF can also do that. We can find the problem based on the passive detection mode of TCP RTO with the lower overhead and cover the real data traffic paths. Finally, we still have a lot to do with the transmission, including reduce the overhead with raster refactor. Next, we will compile the filter rules into BPF code and execute it in the kernel. Finally, in the new kernel, we need some new handy trace points. At the same time, it's not only limited to transmissions. TCP packet loss latency trace tools we are also developing. Finally, if you are interested in the project, you can follow our SIG. Open source is planning. Thank you all for listening to my topic. Thanks.
Another great talk analyzing TCP retransmissions. Thank you, Tony. And if you have questions or comments for Tony, you can put those into the Slack and we'll get those answered and provide that feedback directly. The next person we have up is Jonathan Perry, and he'll from Flowmill, and he'll be doing a talk on turnkey network telemetry with the Flowmill collector.
Hi, this talk introduces the Flowmill collector for network observability and how this open source infrastructure can help create robust, low overhead eBPF observability collectors. We'll discuss why network observability is valuable, then go over 2 challenges in building the collector and how the collector tackles them, and then do a brief demo. Why network observability? Well, because modern deployments are complex, some having hundreds to thousands of loosely coupled microservices written in multiple languages and application frameworks and running across an ephemeral compute infrastructure. All of these make problems difficult to diagnose. And to add insult to injury, the deployment also changes day to day as services evolve. What you might get from network observability is a real-time map of the application and its dependencies, including where each service is running, metrics on how services and their dependencies are performing, regardless of the programming language and or application framework that services are built with. By analyzing the data, you can get a list of important events. And because network telemetry is granular, it is possible to drill down to an individual pod or host level. One of the challenges building a collector was that it was insufficient to just collect information from sockets. One of the major advantages of network monitoring with eBPF is that you are able to see not only IP addresses, but also the context of the communication, the process, container, and host associated with the traffic. To make the telemetry really valuable, more metadata is required. Information about the host from the cloud provider, information about containers from Docker and the orchestrator, and information about network address translation and a mapping of external addresses to names that users understand. The Flowmill collector includes all of this instrumentation. The great news is that much of this instrumentation is reusable for other types of eBPF observability. For example, if you wanted to monitor context switches, collect some profiling information, monitoring files instead of sockets, or monitor system calls, this metadata is still useful. Another challenge we faced was how to reduce overhead. We measured live systems, and for every container update, there were thousands of process and socket updates and hundreds of thousands of socket activity reports. As you can imagine, if you encode container information on every socket report, you could be spending a lot of time fetching, encoding, and decoding container metadata. The Flomo collector only sends updates for container, process, and socket metadata. Those updates are cached, eliminating much of the redundant work. This is one of several design decisions that enabled the collector to achieve low CPU and network overheads, so users can get always-on granular reporting in production. These were not the only challenges we encountered, but for lack of time, let's switch to a demo. In this demo, we will run the OpenTelemetry collector with the Flomo collector. Let's first run the OpenTelemetry collector, which will output metrics to the screen. Now run the Flomo eBPF collector, which will connect to OpenTelemetry to send the telemetry. And now let's look at some of the logs that are output. Here's the kernel version that the host is running. Information from instance metadata, like the instance type and instance ID, and information on the VPC ID and private and public IP addresses. Containers being created on the system. Metadata from Docker. Here is the image ID from Docker and the name that Docker assigned the OpenTelemetry collector. Processes, here's Bash. And sockets, this is socket 232 and the process ID that it belongs to. And here's the same socket and more metadata, source IP address and source port. It's port 22, it's part of the SSH stream that is used for this demo. And here is some telemetry flowing from that socket. You can see it sent 5 kilobytes of data in 11 packets. There is quite a bit of infrastructure required to build a robust, high-performance network observability collector, and the Flomo collector is now available as an open source project with a permissive license. So if you're looking for a network eBPF collector, please go ahead and try it out. We're working to contribute the collector to the OpenTelemetry project to be its eBPF collector, and I expect the integration with OpenTelemetry to become much more streamlined. If you're interested in this work, please join the eBPF workgroup in OpenTelemetry or reach out on Slack. Channel details are on the screen. Thanks for listening.
Thank you, Jonathan. Always awesome to see ways that people are, gathering the context of what's happening inside of eBPF and trying to get it out to the place where we can start using it for analysis and other things like that. This next talk is by Nate Foster from Barefoot Networks, and he's going to talk about eBPF and P4 better together.
Hello, my name's Nate Foster. I'm a computer science professor at Cornell University and a research engineer at Barefoot Networks, an Intel company. Today I'm going to tell you some ideas about how eBPF and P4 can work better together. On the face of it, eBPF and P4 might appear to have little in common. eBPF is a low-level language organized around general-purpose constructs like registers and bytecode instructions, whereas P4 is a domain-specific language based on custom constructs like header types and pipelines of match action tables. But despite these differences, I'd argue that all of us in the eBPF and P4 communities are really fellow travelers on a common path. Our shared and somewhat revolutionary goal is to invert who's in charge of the infrastructure, whether it's the Linux kernel or the network fabric, and make it something that can be programmed by ordinary developers. The natural endpoint of this revolution is an end-to-end programmable platform where every component on the full path, from the application at one endpoint all the way over to the other side, is something that we can program directly in software. And the ramifications of such an architecture is something we're just starting to explore. You can imagine migrating part of the networking stack to a SmartNIC or a programmable switch, or combining application-level observability, something the eBPF community is quite familiar with network telemetry, something the P4 community works on, to get unprecedented visibility into performance issues. But to get to this vision, it's clear that we need to leverage the strength of both frameworks. Being able to program the individual components by themselves is not enough. And so today I want to look at two pieces of technology, in particular compiler technology, that can help P4 and eBPF work together in a larger system. So the first and perhaps most obvious direction is to compile P4 to eBPF. So why is this interesting? It might seem rather trivial, in fact, because eBPF is general purpose and P4 is restricted. But there's a growing body of P4 code for standard protocols and for common network functions. And having a path for being able to execute this code in the Linux kernel would be powerful and would have broad appeal. So in fact, there's already a number of projects that are exploring these kinds of compilers. There's a simple eBPF backend that's distributed with the open source P4 compiler, and there's a more sophisticated, fully featured compiler that goes to the eBPF XDP hook. And there's even a new user space BPF compiler that was released just this past year. So I think all this is exciting. And what we need, of course, are applications and use cases to drive these frameworks forward. But there's also some deeper questions, like how we can leverage P4's restricted model to enable advanced optimizations, or how we can streamline the task of building these compilers so that every new eBPF hook doesn't require a new effort. Going the other direction, here the challenge is to take a general purpose program, maybe written or compiled with eBPF, and accelerate it using a pipeline specified in P4. So there's many ways to do this, but the approach that I've been exploring with my group at Cornell is to use just-in-time compilation. And JIT compilation is something that the eBPF community is familiar with, of course, but we think it's a good fit for accelerators too. In particular, by specializing the program to a particular packet or flow, we can do aggressive optimizations, often shrinking and simplifying the program that we need to run, and simplify the task of lowering that program onto the kinds of quirky instruction sets that accelerators support. Now, the open issue with any kind of just-in-time compiler is that there is a kind of fast path, slow path distinction. And in the context of a networking system, you might not be happy if the performance of your system varies greatly depending on whether it's the first packet in a given flow or a later packet. And so we need to find ways to smooth out these performance discrepancies and make things more predictable. Just to give you a taste of what this looks like, we've prototyped this JIT approach in something we call JITNIC. It's based on some Xilinx Alveo U250 FPGAs. But what we have is a P4 programmable pipeline that runs at 100 gigs per second. And then we have a compiler in a system that maps incoming traffic onto the accelerator while running a residual program to manage state and run the compiler itself. And even on complex applications like a virtualization stack or an in-network cache, the compiler is able to quickly adapt and map the bulk of the packet processing onto the accelerator. So the graph you see here on the lower right shows for our virtualization stack a number of statistics. How many flows are being run on the NIC, how many flows are being run by the compiler on the coprocessor, and how fast the NIC is being updated. And these results are preliminary, but we think they're promising. Okay, so that's all the time I have. Thanks for listening. If finding ways for P4 and eBPF to work together sounds interesting, get in touch and let's get to work.
Awesome. Thank you very much, Nate. And that was a great talk. It had a lot of, it gives us a lot more context over some of the conversations that we had with Daniel earlier in one of the keynote sessions, so kind of describing what P4 and eBPF can do together. I thought that was a great presentation. Our next talk is by Kanthi Pavaluri from Walmart, talking about high-performance load balancing.
Hello, everyone, and welcome to the talk on high-performance load balancing at Walmart. Quick intros. My name is Karan Dalal, and I am an engineering manager with the traffic platform team at Walmart Tech.
Hi, I'm Kanthi. I'm a software engineer associated with Walmart, and I'm passionate about developing networking solutions at scale.
We both work on the LEAF project, which focuses on developing eBPF solutions for Walmart. We are actively working to open source the work that we have done as a part of this project. We are hiring, and you can follow us on the Walmart Tech Medium blog. Layer 4 load balancers are a critical part of any edge or service routing stack. The primary objective of a layer 4 load balancer is to spread incoming connections across multiple servers as efficiently as possible and minimize disruptions in connectivity during changes in servers. In this slide, we have outlined some of the key requirements we considered when coming up with a layer 4 load balancing solution. The first one on the list is ultra high performance. Most of the use cases of a layer 4 load balancer, whether it is at the edge or in front of a service, require it to take an extremely high volume of traffic. So it is important for the solution to be highly performant in terms of latency and throughput. The next one is DSR, or direct server return, where we send responses directly to the client so that the load balancer does not need to handle returning packets, which are typically larger in size. By consistency, what we mean here is the ability to run the solution on commodity Linux servers that can make the solution fit a variety of use cases or cloud environments. For example, supporting virtualized or cloud native or bare metal workloads. The next one talks about how each of the LB node should be able to maintain its own state and create a resilient HA environment where all the LB nodes can serve traffic for all VIPs. Scalability refers to the need of scaling in and out based on traffic estimates. And by ease of maintenance, what we mean to say is that the solution should be able to manage the backend flows seamlessly during a planned service maintenance. From an observability perspective, real-time view of the state of the load balancer service and the traffic that it is managing is really important. Last but not the least, the solution should be extensible, which means it should be possible to add complementing features like rate limiting without relying on multiple products doing bits and pieces.
With a new multi-cloud model, wherein we started building more data centers, we got the opportunity to evaluate the technology choices that are available in-house and in general in the space. First one is hardware load balancers, which have been the choice for many years, but these do come with some limitations. One example of this is if we want to enable DSR, the load balancer and the applications have to be in the same network. This is because they use MAC addresses for forwarding. But this model is not feasible as our workloads are spread across the networks. Also, we cannot scale these dynamically, which is needed for the peak traffic events. So next available choice is IPVS, by which we can address few of the concerns, but it lacks the extensibility and observability. And also the performance of the solution is limited. Like it's not the best that's available in the space. And next is our favorite solution, which is eBPF and XTP. XTP works at the driver layer and so gives great performance benefits, especially for network load balancing kind of use cases where all the data is available at the XTP layer itself. It's the best to leverage this and make the forwarding decision from here itself. And another good thing is that there are few open source solutions that are available in this area. So we didn't have to reinvent the wheel. We rather developed the customizations needed on top of the open source solutions. We chose Catran, developed by Facebook, as that implements MATLAB, and it has great lookup speeds and gives a pretty uniform distribution compared to other hashing techniques available. This is how a Catran-based LB solution would work for virtualized workloads. So on the left, there are different clients. These could be end users or internal applications trying to connect to other applications for some service. And this Catran solution can be used for both north-south and east-west traffic load balancing use cases. And there is this network infrastructure that is BGP paired with the LB cluster. All of the LB nodes in a cluster have the same set of VIPs for scaling and HA purposes. This is also an important advantage over the hardware LBs as they operate in active-passive kind of HA mode, but we can operate in active-active HA mode. Each VIP is associated with a set of service endpoints, and these VIPs are advertised to the network infrastructure over BGP. So the incoming requests are spread across the LB nodes uniformly using ACMP, and no matter which one gets the request, they all are processed identically. This is achieved using two key tables. One is consistent hash table and one is connection tracking table. This whole block is Catran's forwarding plane that is attached to the XTP hook. The consistent hash table is populated as and when the VIPs and the backends get configured. This is populated using MATLAB such that each backend makes equal number of entries in the table or as proportional to the weights configured. And the connection tracking table is LRU based. So when the LB gets a request, it looks up in a contract table. And if it's the first packet in the flow, it doesn't find a match, hence looks up the consistent hash table to get the backend. And this entry is added back to the contract table. So for further packets in this flow, it can be served from the contract table itself. This contract table also helps in making the service maintenance seamless, as the existing flows can continue to go to the backend that's being taken out. So once we determine the backend, we encapsulate it using GV and forward it to the backend using XTP TX, which is forwarding on the same NIC. And the request finally reaches the backend. Now we can configure the tunnel endpoint on them. So the packet is decapsulated and consumed, and the return traffic would directly go to the client, as the inner packet still has the same source as the client. But this solution is not quite feasible, especially if we have a multi-tenant environment and the tenant infrastructure is managed by themselves. So we can run an eBPF-based agent and associate it with the tap device on the hypervisor that can do the magic needed. So the solution becomes transparent to the tenants. But the agent is not yet open source and hence is out of scope for this talk. It's just kept here for the sake of completion. And the last thing is the health check engine. Katran has basic health checking feature, but if you have a large scale environment, you can have your own distributed health check engine and associate it with Katran. So it can tweak the backend weights and control the forwarding logic based on the health checks. There are also some real-time stats that are available in the form of BPF maps provided by Katran, like packet counts, byte counts, cache hits and misses, etc. And we can add more as we have full access to the packet at the XTP layer. So we use Cilium's GoBPF library to manage these maps and export the data to Prometheus to get the needed observability. Let's do a quick demo to see Katran in action. Here is how my setup is going to look like. It's an all Vagrant setup where I have a client, and here is a Katran cluster comprising of 2 nodes, and a VIP is configured on both of them. And that VIP has 2 backends behind it. So whenever a client sends requests to the VIP, it will be routed to one of the Katran nodes, and the Katran node will make sure that the load is distributed uniformly among these 2 backends. And these 2 are my Katran nodes, Katran 1 and 2, and these 2 are my backends. And you can see the configuration here, a VIP, and then these 2 backends, and same goes for the other node as well. And here is my client, and I'm just trying to send a simple curl request. The client says eBPF is awesome, and the server says GMTA, and it is responded by the backend 2. Now it's responded by backend 1. We can also see some runtime stats provided by Katran, which shows the packet count and byte count. There are also some useful metrics that are available in the maps. If anyone wants to troubleshoot, these are useful. Now we are moving on to scenario 2, wherein we create persistent session between the client and the server and bring one of the Katran nodes down. Usually BGP will be configured, and that will make sure that the route is not advertised from this particular Katran node which has gone down. But since I don't have BGP configuration, I'll be tweaking the static routes to replicate it. First, starting a persistent session. And we can see that Katran 1 is taking the traffic. And the requests are being served by backend 2. Now I'll play with the static route to replicate Katran 1 going down. We can see that the session is still existing. It's not broken. And the traffic is now being handled by Katran 2. Moving on to scenario 3, where a backend has to be taken out of rotation for maintenance, in which case we will be updating the weight for this particular backend as 0. And we should notice that the existing flows would still continue to be processed by this backend, but the new flows should go to the healthy backend. Now let's start a persistent session. This one is going to backend 2. And I will update the weight of backend 2 as 0. And the session still continues. Yeah. We can also see that the new sessions are going to the other healthy backend. So that's a quick demo. Thank you all for joining our talk. And thank you, Cilium team, for organizing the session.
I agree. That was a great demo. So thank you very much for bringing that amazing demonstration and insight into high performance load balancing at Walmart. Now we're going to go to a break. We're going to come back at 11:05. And when we return, we'll be exploring we'll be doing another live solving session with Tabitha Sable and the solvers. And so I'm really looking forward to that. Welcome back. I hope you were able to get some exercise, stand up, stretch those muscles, and get your brain in gear for the next session, which will be a live session where we try to solve the second challenge of the CTF. Before we jump to that, I'd like to talk to Thomas, or have Thomas present a little bit about some of the background of the CTF that we did for this show.
Yeah, so I'd love to give some background on this. Running the CTF was actually originally proposed in one of the survey feedback forums that we have run in the last year's summit. But there's more to this story that I would like to share. We liked the idea so much, and that sparked an internal effort at Isovalent that we started organizing an internal CTF all around eBPF and Cilium to provide an opportunity for all the new coworkers we got to learn about eBPF and Cilium and kind of get them up to speed. We called this ISO Games, ISO Games. We had so much fun with that, so we decided let's bring that to the summit. So the challenges that you are seeing today, that the teams are solving, they are modified versions of the CTF style events that we have been running internally for fun and for learning. And we do have more of them. So we might come back with more if you give us positive feedback. So please fill out that survey form. Let us know whether you're liking the CTF, what you're liking, what you're disliking, what could we potentially improve. But yeah, that's the background story on it.
Awesome. And remember that the third challenge is up right now. So if you haven't checked it out, definitely check that one out. And now here are Tabitha Sable and the solvers.
Hello, eBPF Summit. Thank you. Welcome back from break. And thank you for joining us for another day of live solving one of these CTF challenges. In this particular one, here we are. We're in a situation where now we have access to the enemy's computer system, but also we don't quite have what we need. We're in the right place, but the situation really isn't right. So we need to see what we can do to help to bypass this imperial advanced protection. So I'm Tabitha Sable, Kubernetes maintainer, security strategist at Datadog, CTF player, and with me are a team of 4 solvers, a couple of whom are spoiled, a couple of whom have never seen this before, and they will introduce themselves.
Hi, I'm Joe. I'm based in the San Francisco Bay Area, and Bash is my favorite language because it's just the duct tape that holds everything together.
Hello, I'm John. I'm based in Oregon, and my favorite language is BPF-C, very particular type of C.
Hello, everyone. I'm Quentin. I'm working from Cambridge in the UK. I find it difficult to tell what language I prefer. I just know it's certainly not JavaScript.
Hey, I'm Sebastian. I'm joining today from Zurich, and my favorite programming language is Whitespace.
With all this, I feel like I have to speak up in favor of awk because it's never really the right solution to any problem, but over and over in my life, it has proven to be a sufficient solution to a great many problems. And I can't resist the love of a write-only programming language. There have been so many times where I've had to come back and maintain something that I wrote and look at it and just say, well, it'd be easier to do this again than it will be to understand what I did before. Let's start from scratch. So I wouldn't exactly say that's a positive aspect of it, but it's certainly an aspect I enjoy. Joe, I think you're driving. So here we are.
Yeah, so we're at the control bridge for the Grim Hornet. We've got the login shell here, and we can see, you know, a big scary warning from the Imperial Empire about our access to the server can be punishable, but we're just going to disregard that for now.
We've already made so many other choices that are punishable by imperial law. What's one more?
Exactly. So yes, we want to disable the fleet. We need to get this password, and we can see here it's stored at well, it says it curl localhost 1977. So I'm going to do the super naive thing right here and just like run this command and see what happens. Oh, okay. So we're getting a connection refused. All right. So this is kind of interesting because it means that something's actively responding to our request and actually rejecting that. So I guess the question is like, you know, what could be doing that? So we have another hint actually here. Diagnostic tool TCP connect.bt is loaded and ready to be used. So let's run that. Let's see what happens. So it is. All right. It's attached. It looks like there's a couple of interesting error warnings, but we have a some sort of a listing of what's going on.
What is this TCP connect.bt?
Yeah, so I mean,
I think BT stands for BPF trace, right? This is a BPF trace program.
Yeah, so it looks like a BPF trace program that I guess attaches to TCP connect events and then does something. So if we actually run our command again, I think what they'll do is like launch another TCP connection, and maybe we'll get some output coming in through. Okay, so we run it a few times. We can actually see these entries coming up and a PID of our curl process. It's trying to connect to some port. Well, it's from port, and then destination port is 1977. So we can see the connect is happening.
What's it look like on the network?
It's interesting that your connect is refused, but your tool there is telling you the connect is happening, right?
Yeah, so I mean, I guess it depends on what the TCP connect is doing. I mean, I guess we could dive into that, or we could dive into what's happening on the network and see what the packets are doing. What do you think?
Give it a TCP dump or something.
TCP dump, all right. We can do that.
Yeah, why not?
That uses BPF too.
See if we get a three-way handshake or not.
All right. We'll just listen on any interface, I guess. Oh, we don't actually have TCP dump. Well, we can install it.
Can we install it? Cross our fingers.
Yeah, as long as that's not blocked. Okay, so this is not a super locked down imperial distribution, but that's okay.
Somebody left the root account open.
Well, I mean, we're clearly somewhat trusted. That's because we wore those stormtrooper uniforms when we got here. Nobody could see my hair underneath the helmet.
All right, so we'll run that curl one more time. We'll see what's happening. Okay. And so what this is actually saying is, it's kind of, I mean, it makes sense if you know how to interpret TCP dump output, but if you don't, then that's fine too. What we're seeing is the connection from this localhost loopback 127.0.0.1 IP address to the server that we're trying to connect to, and it actually says like, so we've got the SYN TCP SYN going out, and then we're getting a reset back.
Can you check if the server is actually running? Like the server is running a local host, right? So this is a process that we should see.
Yeah.
But is it L?
Because I remember in the challenge, I think you can either use netstat or SS, for example. I think mine is L for listen.
Well, I thought -A. Okay, there we go. So -A is absolutely everything. Admittedly, we're getting like netlink connections and stuff like that in here, so it's a little
kind of
noisy.
odd show.
It looks like
I did this challenge before, or at least I looked at it before, and there should be a process running here. So I think something in our preparation here went wrong.
Okay,
so maybe the Empire
like
actually has upgraded their login shell or something.
Can we like PSEF it or something? See if it's there.
Yeah.
Well, actually, I'm not seeing anything. So we've got my TMUX client, we've got our TCP dump, and we've got the PS. So yeah,
if we start the challenge.
Yeah, if we've got a broken environment, that's fine. We can jump out of here. We can run that one more time. Let's see. I will jump over to here. There we go.
I guess the Empire really upgraded their security system.
Yeah. Okay.
Or the Empire had a botched rollout.
Also possible. Yeah, make sure there's no other container running.
Let's make sure we use root. Cannot connect. Stop the container before. Do we need a force remove?
I think you just have to stop it first.
Docker.
-F also should work, yeah.
All right. ps-a. Okay, so we don't have it running anymore. Let's try this again. Okay, that's a little unexpected, but that's okay. We can roll with it. All right, so we got access again.
Do your PS again and see what we have.
Yeah.
Right.
All right, so we've actually got a whole bunch of defense trades going on here.
Oh, there we go. Now do your curl again and see what happens. Yeah. Or.
Yeah. Okay. So let's go curl localhost 1977. I mean, I guess it'll fail in the same way, right? Like before we were having it fail as well. But yeah. So what else do we have? So it's just, I mean, there's a lot of these. I mean,
there's a swarm of them.
So we ran the TCP connect hook before.
Oh, there we go.
We didn't see any. Oh yeah, it's running there. Yeah, nice.
Yeah.
So we ran
Just
the
make
TCP
sure it's
connect
actually
hook before.
working. Yeah.
So the TCP connect hook, that's a hint, right? So let's see if this now gives us something more interesting than before.
Yeah, yay, it's listening. Awesome.
Okay.
Do you want to try and connect?
We have
to
several listings. Yeah. So when we did the curl again, just do that. So we're getting connection refused. So that's just like last time, but we can actually run the BPF trace, I guess, again as well.
You're going to need to split your screen again.
Yeah, let's just do this. Momentarily, I will just SSH into the right VM here. The demo gods are not always happy with everyone, so but it's quite okay. So I think we can do a Docker exec into that same container, right? So UTF-3
should be
any
able
other parameters there. Let's get a bash.
I think you'll need IT and bash.
UTF-3 -- name.
Did you give it a name when you created it, or do you need to pass the hash?
You just do a Docker PS, right? And then then just pull the full string. The ID will work as well usually.
Just this one here.
Yeah.
All right.
Right.
There you go.
Yeah, let's try that tracer. You don't have any history.
TCP connect, right?
You have no names, man. No names.
All right. So okay, and actually, we're not getting those weird errors now either. So
oh, that's a good sign. Yeah, what happens now?
So yeah, let's run that. Okay. So we see the same thing again. Actually, we see.
Look closely. Do we see
Is it the same thing though?
Actually, that's interesting. So we see it connecting to 1980. But what's happening on my actual connect is 1977. So somewhere along the way, that TCP connect is getting rerouted to the wrong port. That's interesting.
That is interesting. Who could do that? Who would do such a thing?
BPF tool.
There was a head about BPF tool, so yeah, maybe we should take that on.
Oh yeah. Let's have a look at that.
I think you're gonna have to Control-C to kill the. Yeah, there you go.
So, oh yes, okay. So we have BPF tools, so we can see what progs are attached, I guess. Whoa, this is interesting. So okay, so we got a kprobe connect hook. It's a GPL program. It's nice to know. We can distribute it, and it's got a whole bunch of metadata here about how it's that's the advanced protection. Okay.
Well, what does this thing do? Do not attempt to bypass these protection measures.
Yeah. Article A57. Yeah, so what does it do? So it's a kprobe. It's named Connect4 hook, so I guess it's probably attached to the Connect hook. I don't know if that's listed anywhere else here.
Can we list out the bytecode for this thing? Like, can we decompile this thing with BPF tool?
Yeah, I think that's the dump exploited name connect. Awesome, we've even got autocomplete here. All right, so we're diving into the assembly code now. All right, so well, we've got annotation, so that's going to make it a little bit easier. So we have like a probe read user BPF helper call going on here. We've got some like source address import comparisons going on here. We can actually see the comparison against the number that we're trying to connect to. So if it's equal, then we're actually going to swap it out. So this TCP connect program is actually swapping our address, but only if we connect to 1977.
This is not our friend.
Can we just blast it away?
If you,
I would love to.
Yeah, do we have a suggestion?
Yeah, if you look at the output when you list the programs, I think in the left column, you had a bunch of numbers, and there was one saying hint, close to HT.
Oh, interesting.
I have a feeling the empire might be compromised.
All right, well, they can take a look at that. So is it sys fs BPF defense droid? Okay, so we've got docs. I mean, this is what more can you ask for? Okay, so it's a series of characters, and it's
so this is FS. What is
Let's
this
use
is
awk. Come on.
You want awk?
Sure. Cat that thing. Pipe it to sed. Let's use. I mean, you can sed and
I mean that's actually not too
single quote
too bad,
and comma. Replace them with nothing.
That's what is it?
It's in the BPF virtual file system, so maybe it's a BPF map. Could it be a path to a BPF map?
Sys fs BPF. Oh yeah.
Oh, so you got a problem because you try to put a single. Oh, well, you think we can read it out the map?
I think BPF tool has some functions for this, right?
Yeah, map dump.
BPF tool map dump,
and that's pinned, and then the path.
Okay, let's try that out. Aha, that's a little easier than our SED. My SED foo is maybe not as good as you, Tabby. All right, so it comes with observability tools. Okay, so in case of failure, we can use this program installed in the path panel. We have the system logs for detailed messages. Okay.
Oh, and we need to look at the feature designators. We need to look at the FDs.
So let me think. So the program that we know is a K-probe, right? So a K-probe, like BPF programs need to be owned by something. So I'm wondering kind of, so like you guys are more of the experts than I in BPF, but I think there's one way is having it in the file system, which doesn't seem to be the case here. The other one is having it in the FD in a file descriptor.
Oh, so I think that the file descriptor says something BPF. Can we do some nasty like ls-l proc star fd and then like grep for BPF?
You're saying like list basically all the processes on the system, try to find the FDs associated with them, and then see if there's like a BPF string in the file name. Is that what you're thinking?
Yeah. Like if you do an ls-l on proc star PID, then you'll see. Yeah, proc star FD. Sorry,
FDs, right?
Yeah, because star is
we get a whole bunch of stuff here. And you're thinking just grep for BPF here? I mean, we do actually have a
BPF program. Do we have less? Can we search backwards to find which PID it is? Okay.
We can use a little more grep context.
A little more context.
So that was actually process 352, which I guess we can find out what that is. Peeker, is it? It's one of our defense droids. Okay. Can we just kill the defense droid? I mean, we did see there was a lot of them. But,
there was a warning that if you kill the wrong defense droid, the system might be terminated, but I think it's worth it.
How many times do you live?
Yeah, life is short. No time to waste.
All right, let's do it. Get my blasters out.
Yeah.
All right. So what are we expecting to happen there? So we were expecting that the BPF program associated with that defense droid has disappeared. It's gone.
Yeah.
So if we do like a prog list again.
Like a prog list.
Let's do
There's
it.
no programs attached anymore, right? So I think we can go back to our original curl and just connect to that server. All right.
Nice.
Yes. Nice. Congratulations. Thank you. Thank you so much. This was super fun. We have hit right on time. And so now we're going to turn it back over for the introduction to the next series of talks. Thank you all so much for joining us. Thank you, the four of you, for hacking this with us. And maybe we'll see you tomorrow on ECHO.
Thanks a lot.
All right, thank you.
That was amazing. Giant round of applause, emojis, go crazy with them in Slack. I think Tabby and the solving team did a terrific job there. So we are moving into a section about actually writing BPF programs. Up until now, we've mostly been talking about using them, but now let's get into what happens if you want to write the code yourself. And first up in this series of talks, we've got Kyle Quest from slim.ai, and he's going to be giving us an overview of the different BPF library ecosystems in different languages.
Hello, everybody. Let's explore the library ecosystem for eBPF. So you want to build an app, but you don't know much about the available options. Should you bite the bullet and go with one of the C libraries? Should you try your luck with one of the libraries in your preferred language? This talk will get you one step closer to choosing the libraries that work for you. Hopefully, you're not thinking about a BPF app in Java or PHP. If you are, you'll have to write your own library. Good news, this talk will give you a few ideas too. Here's the list of libraries we'll explore. A bit of background before we get started. When you create a BPF-based app, you need a library that will load and ideally attach your program to the right hook. You'll also want a library that supports the I/O needs for your application using the map, perf, and ring buffer constructs in BPF. And if you're new or if you're not comfortable writing BPF programs from scratch, you might benefit from the libraries that help you build the programs using higher level constructs. In this talk, I'll focus more on the BPF program attaching capabilities for different program types to help you choose the library. As you know, there are different BPF program types. Each type can be attached to a different part of the Linux kernel. The program types can be grouped into categories. The most common categories are tracing or profiling and networking. You'll find the list of categories at the end of these slides. Let's start with the most basic libraries. They're low level, but they provide the foundation for many other libraries. BCC is the most mature option with the biggest community. Good option to build V1 of your tracing app. libbpf is the official low-level BPF library. Good option if you don't want to compile the BPF programs at runtime. The starter project makes it easier to develop your app in C, even if your C is a bit rusty. Quite a few Go libraries out there. This is the official BCC wrapper. Doesn't seem to expose everything in BCC. Provides good coverage for tracing apps though. This is not a wrapper, which is great if you're worried about CGO slowing down your app I/O. Interesting features, but the API is a bit confusing. Strange that it doesn't support attaching XDP NTC program types given its networking roots. This is also not a wrapper. Too bad it only supports kprobes for tracing. I like this library more than the previous library. This is a libbpf wrapper. Great option for tracing apps given its origins. There are a couple of libraries for Python, and only one of them works as is. This is the official BCC wrapper for Python. Tons of sample code, great option to prototype your first BPF app, especially if it's a tracing app. eBPF is built on top of the BCC wrapper. It allows you to define all parts of your app in Python, but it needs work and it only supports kprobes. Rust has a number of interesting libraries, and not all of them are wrappers. This is a lightweight wrapper for libbpf. It's used for the libbpf bootstrap examples in Rust, so it sort of makes it an official wrapper. This is another libbpf wrapper. It re-implements some of the program attaching logic. Should be okay for tracing apps if you don't need raw trace points. Red BPF probes to build BPF programs looks interesting. This is a pure Rust library, very ambitious, lots of potential if they can pull it off. Supports more BPF program types than I expected. Good for tracing and low-level networking apps. Aside from the Lua library, you'll need to invest a bit of extra time to make these other libraries work. This is the official BCC wrapper for Lua. Even this library has a few rough edges. There's a third-party library for Ruby that wraps BCC, and there is a BCC wrapper for Node.js as well. If you're writing a tracing app, especially with kprobes, almost any library will be okay. If you want to write a tracing app that won't break with different kernel versions, make sure you pick a library that supports trace points or raw trace points. XDP is the most commonly supported network program type. However, not all libraries will attach these programs for you. Keep that in mind. If you don't want to compile the BPF programs when your app is deployed and runs on the target machine, then don't choose BCC or one of its wrappers. Thank you, and feel free to reach out if you have any questions.
Thank you, Kyle. And don't forget, if you've got questions, post them into the eBPF Summit channel on Slack, and our speakers are all there hoping to answer your questions. So following on from that talk about a range of languages, we're going to concentrate on Rust now with Alessandro Decina from Deep Fence telling us why Rust is increasingly a good option for eBPF programming.
Hello, I am Alessandro, and I have been working on Rust and eBPF for a few years now. I'm going to show you what writing eBPF programs in Rust looks like today. I started working on eBPF in 2019. I wrote large parts of the Red BPF library, and then I also wrote Cargo BPF, which is a program that at the time was needed in order to build Rust code to eBPF bytecode. I then moved on from those projects, and I started working on adding eBPF target support to the Rust compiler itself. That work was finally merged a couple of months ago. So all you need today in order to compile Rust to eBPF bytecode is just the regular standard Rust compiler. Then also at the beginning of the year, I started working on a new library that I also released a couple of months ago called Aya. The reason why I started working on Aya is that I wanted to build a library that was built with a strong focus on operability, ease of deployment, and developer experience. Aya is built entirely in Rust. It does not need a SQL chain or kernel headers to build. It does not link to any external libraries. It's completely self-contained and very easy to deploy. And even though it's a relatively young project, it already provides an idiomatic and safe API for most of the features exposed by the eBPF platform, including PTF. The easiest way to get started with Aya is through the cargo generate program. So if you run this command on your terminal, it will generate some basic boilerplate, and it will prompt you for a project name, and it will also generate some simple example code. The example code looks roughly like this. As you can see, the code is split in 3 sections. At the top, we load the eBPF bytecode. Loading entails running relocations and creating maps and doing everything that is needed in order to run programs later on. And then in the central part, we get a reference to a map and we insert a value in it. And then at the bottom of the program, we get a reference to the XDP program we want to run. We load it and we attach it to a network interface. To build the code, all you need is to run cargo build. This is the standard Rust build command. And because we want to generate a statically linked binary, we use muscle as the target. As you can see, this builds very fast. And yeah, if you verify with LDD, it actually depends on nothing. So that was the user space part of the code. But what about writing the kernel side eBPF code in Rust too? First of all, a lot of people ask me why bother doing that at all. If the verifier already enforces memory safety, then what is the advantage of using Rust over using C? And the answer is obviously that there's a lot more to Rust than the borrow checker, right? Rust comes with a very powerful type system. For example, in AYA, we're able to provide a strongly typed API for maps, for helpers, for programs, for pretty much everything. Whereas if you work with maps, say, for example, in C, you know that you end up working with a lot of void pointers. Rust also comes with some very useful types, including slices, byte slices, or the result and option types that are especially handy when implementing error handling. And if you've written eBPF code, you know that you end up implementing a lot of very strict error handling in order to pass the verifier checks. And then finally, one thing I'm super excited about is all the tooling that is in the Rust ecosystem. We've already seen Cargo and Cargo Generate, but the thing I'm mostly excited about is that the eBPF code you write with Rust can actually be uploaded on the Rust package index. And so over time, I think that we will be building an ecosystem of reusable eBPF code. This is what the actual eBPF code looks like. So you can see that at the top, we define a global map. We annotate it with the map macro attribute. And then we define an XDP program annotated with an XDP macro attribute. And then the logic of the program is very simple. For every incoming packet, we get the TCP destination port. If the port is blocked, we block the packet. Otherwise, we let it pass. And to build, again, you can just use Cargo. You use Cargo xtask build eBPF to build the eBPF code. And then you use just regular Cargo build to build the user space code. And that is pretty much it. If you're interested in what you saw or in AYA, AYA is developed on GitHub. The documentation is on docs.rs. We have a Discord channel where we discuss development. And finally, if you want to reach out to me, you can find me on Twitter. Thank you for watching.
That was great. Let's have a round of emoji applause for Alessandro. And then next up, we're going to be hearing from Lorenzo Fontana, and he's going to be exploring how are BPF helpers made.
Hi everybody, I'm Lorenzo Fontana. Welcome to my session, How are BPF helpers made? The first thing I want to talk about is what's the reason why we need to know how they are made? But, well, might be because of curiosity, just for fun, but more importantly, to understand how the BPF works and what it does underneath. And also because I asked myself this question while working on something, and I just wanted to avoid to all of you just to do the same thing again. First of all, what are the BPF helpers? Those are kernel-defined functions that can be used to perform specific tasks, right? Accessing data from a map or getting the current process PID, writing to a map, closing a file descriptor, these kind of things. And they are called directly from BPF programs. And they are effectively the only way to interact with the current specific execution context of the program. This is not true anymore some way, because now you can also call kernel function directly with recent kernels, but still this is 99% true. And in my opinion, they are very similar to syscall, and conceptually they are just a way to call kernel functions. So it's just a way of interacting with the kernel like syscalls are. First of all, how do you call a helper, right? The way you have seen it in examples around there might be this, or if you use the CDMBPF library, it might be the equivalent in Go, but you just call a function, right? In this case, BPF get current PID TGID, and in this case, you also shift 32 bytes because the process ID stays there and after 32 bytes, but that's not important. Pretty simple. Should be working, right? Not necessarily, because for it to work, you have to either include the BPF helper sage from libbpf if you have it installed, or you just don't have it and you have to declare it yourself. And if you want to declare it yourself, you just open the libbpf header or the VM Linux sage header. You will find something which is was like What does it do? You just void pointer to 14. What 14 is, right? You just don't know. You just have a function definition that is just a pointer to function defined as 14. The same call can, if you convert your program to assembly, can be seen there. Just call 14, and R0 is the register where the result is. In this case, it's shifted 32 bytes, or in helper with arguments like perf event output, you, before calling 25, which is perf event output, you will also need to pass all the parameters, right? Like the context and the size and everything. But, let's go to the, juicy thing. How do I implement helper? It turns out to be very easy. You just define a function using a macro, depending on the number of arguments. BPF calls 0, 1, 2, 3, 4. You can have, and 5, you can have maximum 5 arguments by convention. In this case, is the implementation of BPF get current PTGID. You implement helpers in kernel, so you have access to kernel structs, like in this case, the task struct of the current process, and you just extract TGID and PID from there. Easy peasy lemon squeezy. Then you have to define a function proto, BPF func proto, for that function, pointing it to the function pointer that you created. You define if the program is GPL only or not. This is very important because you might, while writing BPF program, you might have noticed that you have to pass the license of the program. And sometimes if the program is not GPL, it doesn't work. You might be asking yourself, how do I know when it works? What are the functions that are GPL only versus what not? If you just grab BPF func proto in the kernel, you will have a better idea of that. And then the return type, integer, can be map pointer, other types, void. And then if you have a more complex function, you can also have arguments, right? Arg1, 2, 3, 4, 5, and they can have specific types. You can pass them. But again, where does the number come from? You remember 14, 25 is just a function mapper, which is a macro. For every one of them, it defines the BPF underscore func constant that we've just seen before here. Here, BPF func perf event output. And for every one of them, it also defines the number, right? So if when that macro is expanded, I went to 14, but there are many more, every helper will have its number. So the kernel will know what to call when you call it. Important notes about what I said: helpers can be implemented anywhere in a kernel tree. They can't be added via out of kernel module code because there's just not a way of hooking them into. So you cannot write kernel module that you load as M in your kernel with this code. And BPF helpers are actually not the only way of interacting with kernel functions anymore. There's an LWN article about that. Now probably supports some kind of TCP functions for now. And useful resources, I just tried to find patches, a patch in the kernel that just implements an helper. The latest one is from Alexei, is the BPF sysclose helper. The link is there if you want to take a look. It's very easy to follow it and implement another one of your own. The Python script that generates and man 2 BPF helpers is also very useful for understanding how the documentation is generated out of the helper that you wrote. And that's it. Many thanks, as always, for listening to my ramblings. See you around. Bye-bye. Enjoy the conference.
Thank you, Lorenzo. So as engineers, we probably don't always want to think about licensing considerations, but it can be important. So the next talk is by Itai Shakouri from Aqua Security, and he's going to discuss the OSS licensing considerations we need to think about when we're writing eBPF programs.
Hello everyone, my name is Itai Shakouri. and I am Director of Open Source at Aqua Security. My team and I built a wide variety of open source projects for the cloud-native security domain. And when it comes for us to pick a license for our software, we usually pick the open source friendly option, something that will allow everyone to benefit from our programs without too much implications. So we usually pick a permissive license such as Apache 2. These are a family of licenses that have the intention to allow the user as much freedom and as little worrying as possible about legal aspects. Basically, just do whatever you want, don't worry about it. On the other hand, there is another family of licenses called copyleft, namely the GPL is one of them. And these kind of licenses say that if you use a GPL, for example, licensed code, your new program, if you distribute it, you have to make it open source under the same terms, meaning under the GPL as well. So you have to kind of pass on the GPL to the next person who might be using your program. This is why it's also sometimes called viral licenses. One of our projects, Tracy, is a runtime security solution, and we're heavily relying there on eBPF. And because we're using eBPF there in Linux, it affected our licensing decisions, and because it's applicable to other eBPF and Linux projects, I thought it would be worth sharing. So let's review the anatomy of a typical eBPF program and how it looks like for Tracy. For Tracy, there is the user space written in Go. This is our choice. We also chose to use libBPF. So this is loading our eBPF probe into the kernel. And let's focus on the kernel side of things because it's more interesting here. The eBPF program probably relies on other pieces of code in order to function. In our case, Tracy is a compile once, run everywhere kind of eBPF program, so we are leveraging libBPF in order to do that. Tracy is also heavily relying on kernel structures, looking into them and dereferencing kernel pointers, so we include a lot of kernel headers into Tracy as well. Another thing that we do, like any other BPF program, is to use the BPF helpers. You know that eBPF programs cannot directly interact with the kernel functions. They have to go through the helpers, and we do a lot of those as well. So let's look at this layout and its licensing implications. So we see that in blue is our application. This is our decision to make how we want to license it. libBPF is licensed it's available under BSD to close, which means that it's already a permissive license. This is why we don't worry too much about it in this talk. The red parts are the Linux code. And this is something that we need to discuss because Linux is not a straightforward licensed application. There are different components that are licensed differently, and you really need to be careful about what's going on there. Let's look at the BPF helpers. This is a snippet from the BPF helpers C file, and we can see something interesting here, that these are two BPF helpers, and they have this field here, GPL only. One says that it's not GPL only, and one says that it is GPL only. This flag actually controls whether your eBPF application can call into those helpers, can use those helpers at runtime. This is actually enforced at runtime, and it's controlled by this section that you should include in your eBPF program. Maybe you already have it because you faced an issue, you Googled for the solution and you found that you need to include this line. Maybe you copied it from some other boilerplate code that you had. Maybe you intentionally added it, but the interesting part is that this actually effectively declares your application as a GPL application, and the presence of this section unlocks at runtime a bunch of BPF helpers which would have been locked from using if it wasn't GPL. It's also interesting to understand that your eBPF program doesn't have to be GPL licensed. It's your choice after all, but you will be restricted if it is not. In our case, in Tracy's case, we did choose to license the eBPF probe under the GPL because Tracy uses a lot of different Linux kernel code, and it was the right thing to do for Tracy. One interesting thing to note here is that we licensed the eBPF probe GPL, but we kept the entire project Apache 2 as much as we could. And this is because the eBPF probe is distributed differently and loaded dynamically into the kernel, meaning that it doesn't have to share the license with the rest of the application. In our case, this was the right thing to do. It's also probably the safest thing to do if you don't want to spend too much time thinking about what you should do. Probably GPLing your eBPF code would be a safe decision to make. But this is a good opportunity to remind everyone that I'm not a lawyer, and this is not legal advice. This is just me sharing our process, our considerations, and I just wanted to share it with you in order to encourage you to spend some time to think about your case, to think about how you use the Linux code, the BPF helpers, the helper libraries, and to see how it affects you and how it affects your open source licensing.
Thank you, Itai. And if we do have any lawyers in the room, then make yourself known in Slack. We'll ask you difficult questions about licensing. So next we are back to a fully technical topic. We're going to be hearing from Alan Maguire at Oracle about the BPF type format, or BTF.
Hi, my name is Alan Maguire. I'm on the Linux networking team at Oracle, and I want to talk about data-centric tracing with BPF. So within the Linux kernel, we've got some great tools for tracing control flow. So ftrace is one great example of this. And I've shown the function graph tracer, which makes our control flow actually look like code. So it's very easy to see what's going on. At the same time, debuggers like GDB have excellent support for examining data. So, we can print data structures in depth and we can take a look at what's going on. So the aim here is to bring those two together. So we want to bring that power of debuggers to visualize data, to examine data in depth using BPF. So the key to all this is the BPF type format, which ships with many distros now and provides descriptions of data types, functions, and variables. You can check if your kernel is built with BTF by looking for syskernel BTF. And there should be a VM Linux file there, which has the BTF associated with the kernel, and there should be module-specific ones there if you've got module BTF too. So the BPF has provided for a while a way of dumping data structure descriptions, and this is often used in BPF if you're creating a header, such as vmlinux.h, that describes all the kernel data structures. You've probably used this before. And the idea there is basically that rather than have to include a bunch of different header files, you can dump that header description and include it in your BPF programs, and it saves all the hassle associated with the various issues that can come up when you include a bunch of different files from the kernel. So recently we've extended this functionality to support dumping not just type information, but typed data. So we use the information about the types to dump a representation of the provided data using that BTF information associated with its type. So here's an example. So you can see here we're dumping a struct skbuff, and we're dumping the type information and the actual data associated with the type as well. So you can see both. Here's the function signature for that function. So you have to give it a BTF dump, the type ID that we want to dump, the data that we're using to dump, and the size of the data that's valid associated with that. And then there's a bunch of options which include things like the indent string we use. By default, it's a tab, but you can have a space or a number of spaces. The indent level to start, display at, compact mode, which is effectively just getting rid of the new lines and extra white space. You can skip the names of type members as well if you want to have a very compact output. That can be useful for small types. For big types, it kind of gets a bit hard to track what's where. So here's an example. So in the compact form, you can see here we've just stripped most of the white space away, and in the skip names form, we can't see the names there, so we just get the type data. So to use the API, you need to get your BTF via libBPF, find kernel BTF for the kernel BTF, and then there's other ways of getting module BTF as well. You need to provide a callback function which is going to display or save your dumped information. So in this case, we're just printing it out. So you need to create a BTF dump then using your BTF and your function for dumping the data. Then you have to get the BTF ID that you want that you're going to dump. So in this case, we're looking up an skbuff to get the type ID associated with that. Then we finally, when we have our data from the kernel, we call BTF dump type data with the dump, the type ID we want to dump, the data itself, the size of that data, and any additional options around display. So on the kernel side, you're going to want to keep track of the size of the data as well as copying the data to user space via a perf event or ring buff. You want to know the size because in some cases you're going to be dealing with large data structures which you're not going to be able to capture all of. So being able to let user space know you don't have the whole picture is useful. So I created an example called ksnoop, which is basically a way of snooping entry and return and showing arguments and return values. And so to just see what it can do, here's an example of, we just get the function signature for IP send skb, and then we want to trace IP send skb. So we're going to see the entry and return with all the arguments and return values displayed. You can specify a particular argument by name. So in this case, we just want the skb. You can also specify a member. It just supports one level of membership, so you can dive into the socket within the skb there. We can see that. You can specify the return value, so we use the keyword return for the return value. You can also specify a set of functions that you want to see, but only if they're called loosely in that specific order. So for example, if a call to TCP send message ends up calling TCP transmit skb either directly or indirectly, and that in turn ends up calling IP output, we want to see the output for all of those. So this is useful in cases where you might have a stack signature for a particular failure and you want to dive in and see what the arguments or return values are associated with that failure. So it can also support modules by using module BTF. So if module BTF is available, you can do that. Here we can see we're tracing an IWL Wi-Fi function. So hopefully that gives you a sense of what you can do. There's a lot more that can be done in the future, of course. But for now, you can see more information about BTF, the type dump capabilities, patches on the BPF mailing list, and the ksnoop patches on the BPF mailing list are there if you want to dive into that and actually see how some of this is done in practice.
Thank you, Alan. So now that we've heard about BTF, we're going to move over to Kevin Sheldrake from Microsoft, who's going to talk about auto-discovering kernel structure offsets without BTF.
Hello, I'm Kev Sheldrake, and welcome to my talk, which is about the auto-discovery of kernel struct offsets without using BPF type format. In October, we're going to release Sysmon for Linux, which is a port of the Windows sysinternals tool Sysmon, which is a system monitor tool that generates system and security events and sends them to the Windows Event Service. On Linux, the events will be generated with eBPF and they'll be sent to syslog instead. This is built on a library which we'll be releasing at the same time called libsysinternals eBPF, which is built on libBPF and includes a library of eBPF inline functions that can be used as helpers. Of course, it will be fully open source, and the most important thing is that it will be built once and then it can be deployed to many machines. So before I get onto that, I just wanted to show some screenshots of Sysmon itself. Here you can see you can launch it in exactly the same way as you would on Windows, and when it's running it generates events in the same XML format that is used on Windows. So if you can already obtain and parse the events from the Windows version of Sysmon, then you can probably use the exact same parser to interpret the events that you could pick up from syslog. So build once then deploy. The reason why this is important is because many users of a tool like Sysmon don't necessarily want to have build tools on their production servers. They don't want compilers, tool chains, etc. They don't necessarily want kernel sources there either, or even symbols packages. And a lot of them certainly don't want to recompile the kernel just to run a tool. This means that it's very difficult for a tool to use BCC or BTF core in that kind of environment, because a lot of kernels don't come with BTF already compiled in, and a lot of machines don't have the support infrastructure to make BTF work. So we need an alternative. So what do we actually want? Well, if we're only reporting on the parameters to syscalls, for example, then we don't really need a lot of introspection. We don't need a lot of reach into the kernel structures. But if we want to do interesting things like look up a file descriptor to see if it's a socket or a file, or pull out the entire command line from the task struct, and or even navigate through a process's parent to get the parent's process ID, then we need a bit more reach than we get otherwise. So inside libsys internals eBPF we have a kernel offsets struct, which contains up to 4 offsets per entry, and the way that they work is we take typically the task struct, add the first offset, dereference the entry at that point, add the next offset, dereference the entry at that point, add the next offset, dereference the entry at that point, for example. And that lets you navigate from struct to struct via pointers in those structs. And of course, if we get to an offset which is -1, then we know to stop and that we've got the entry that we require. This is a really simple way of being able to pull out information from those structs based on knowing the geometry of them. So when libsys internals eBPF starts up, the first thing it does is looks to see if there is a configuration file with these offsets in, because if there is, it will use that. These offset files can be generated using the get_offsets module that comes with libsys internals eBPF, which is guaranteed to provide the absolute correct offsets. This is mainly a fallback mechanism in case the other mechanisms don't work. So if the offset file is there, it uses that first, because it's considered that you've decided that the other methods won't work, and therefore you're forcing it to use a particular set of offsets. This does require a tool chain and kernel headers, so in order to be able to run the get_offsets module. If that configuration file isn't there, then it will look up the kernel version in the offsets database, which currently has 1315 kernels and the offsets for them, which were supplied kindly by Project Frita. We simply take the version of the kernel, look it up in the database, and if it's there, pull out the offsets. This is quite likely to work, but only on publicly distributed kernels, because if you've compiled the kernel yourself, then obviously it won't be in our database. But if it's in our database, then it's highly likely to be accurate. So that's a quick and guaranteed method of finding the offsets. But if it's not in the database for whatever reason, then we move on to automatic discovery of offsets, which is the main thing I was going to talk about. And the way I go about this is I use eBPF to perform memory forensics on kernel data structures. Essentially, I attach an eBPF program to a syscall trace point, and I use uname because it's not called very often. I set up some configuration in a map where I give it the userland process ID. Then I call uname. That triggers the eBPF program, and the eBPF program will check the process ID is the one in the config to make sure that it's only talking to our userland program. If it is, it can then find the start of the task struct using a BPF helper, dump memory from the task struct, stick it into the perf ring buffer and send it back to userland, where it can then be searched for known values from which we can then get the offsets. So what sort of things do we search for? Well, the process ID and the task group ID will be the same in our program because we haven't launched any separate tasks, and each of those is a 32-bit number. So because they come one after the other in the task struct, we've now got a 64-bit number essentially, which is unique, and the chances of finding that number otherwise is less than 1 in 2 to the 64. So if we find that number in the task struct, there's a good chance we found the offsets of the TGID and the PID. Equally, we can look from there to find the link to the parent task struct, which will be 2 64-bit pointers with the same value somewhere after the TGID. We can dereference the parent and pull out the process ID and compare it against what we get from get ppid in userland to confirm that we've actually found the right pointer. And another thing we can look for is the process start time, which obviously we know because we've just started the process up, and that'll be in nanoseconds since boot. And again, that is a unique 64-bit number which we can search for somewhere after the parent link in the task struct. Equally, we can look for the COM quite easily, because again that would be quite unique. We can look for creds because we find that the cred struct will be pointing to the same place as the real cred struct, and they are aligned one after the other in the task struct. And if we fork off a child and we set the UID and the GID to particular values, then when we dump the cred struct for that child process, we can look for those values and confirm that we've actually found the right struct. So in summary, the way this works is if you have a configuration file, then sysinternal's eBPF will use that first, because that usually indicates that you either want a guaranteed method of getting the offsets or the other methods have failed, and so you've run the get offsets module in order to obtain those. Otherwise, it looks up your kernel version in the database, and if it's in there, pulls out the offsets that match that. And if it's not in the database, then it uses the automatic discovery process, essentially memory forensics, which is what I've just been talking about. So, as I say, Sysmon for Linux and the sysinternal's eBPF library will be released in early October. They will be open source on GitHub, and if you want to talk to me, ask me questions, or provide us any kind of feedback, then you can reach out to me on Twitter at kevsecurity, and you can also email me on my Microsoft email address, which is kevin.sheldrake@microsoft.com. Thank you very much.
Thank you, Kev. And everyone, let's do some emojis in Slack. Wonderful. So next, let's turn to the verifier, and we're going to hear from Jonathan Bruchim from Flow Security, who's going to talk about turning the verifier from an enemy into a friend.
Hello, my name is Jonathan Bruchim, and I'm so happy to be here. I'm a Linux kernel expert working in Flow Security, a data security company based in Tel Aviv, in Israel. We use eBPF as our core technology, and I'm leading the research and development in the company. Today I'll be talking to you from my personal experience about the eBPF verifier and how to turn it from an enemy to a friend. Okay, so the eBPF verifier is a component in the kernel that verifies our bytecode and verifies that it's valid, validates that our code won't crash. It does things like check memory boundaries, check our stack that it's in a valid lane, check that we use valid helper functions, check that we don't overflow potentially our system. So the verifier is actually a good thing. It makes sure our code won't crash, but it's really, really annoying. We get lots of errors, we get lots of weird logs that some of them just can't understand. And I'm sure lots of you seen that lots of these errors just don't have any solutions on the web. And I worked on weeks on fixing lots of these errors. And finally, after running my code on one machine, I ran it on another one, and it just didn't work. It just got a verifier error. Okay, so now I'll show you an example. This is a Kprobe on TCP send message, and what it does is copy a buffer into a per CPU map element. So we can see that this is a 5.8 kernel. And the sensor just started and everything is good. And this machine is a 4.9 kernel. And when we run our code, we got this error. It expected a frame pointer, and it got something else. And it's really weird because it just worked on one kernel and on the other it didn't. So let's look up this error on the verifier code. So let's find this. Expected equals. The Linux kernel code is open source, so you can just look it up. So expected equals. So this is the source code of 4.9 kernel. You can see one time that this expected equals is found on the check stack boundary. It doesn't seem like it's the place. And the other place, let's see what function it is. Check func args. Seems like this is the right place. Okay, so what we can see here is that the argument that we actually send is a pointer to map. And what it expects is a pointer to stack. That's exactly the error that we got. And we'll look into the 5.8 kernel. We know the name of the function, check func arg. This is kind of the same place. And what we can see is that it actually validates if it's a pointer to map value. So if it's a pointer to map value, it's actually fine, and the code will pass and work. So this is exactly the change that we saw in kernel 5.9 to kernel 5.8. And this is the reason that our code works. So my message to you is that the verifier isn't that scary. When you have to, when you see all these weird errors, you can actually open the code. It's open source. You can get to know it, and like that you can make it your friend. And thank you very much for your time. Any question, anything you want to ask, just mail me or any other way. And thank you.
Thank you, Jonathan. So we are getting to the end of our little series here on BPF programming. The last talk in this section is going to be from Grant Seltzer, and it is about compile once, run everywhere.
Hello everyone, my name is Grant Seltzer Richmond. Today I'm talking about compile once, run everywhere, the BPF dream. I'm on the open source engineering team at Aqua. I'm from Brooklyn. These are my pronouns. You can recognize me on Slack by my happy little crab guy that I have here. So I want to talk about my experience as a developer / maintainer of Tracy. Tracy is a Linux runtime security and forensics tool which uses eBPF to attach to hundreds of different hooks, whether they're system calls or LSM hooks or kernel probes or network events using TC. We read in a lot of information from the kernel to give information back to the user or apply policy on it using our Tracy rules project. So we could see here in this example, execve is being traced, and we're reading in all this information and displaying it to the user. So we can see that Z shell has executed a couple of different commands using execve, ls, and git, and we have all their arguments, and we have the user ID, and we have the process IDs and thread ID, and we have to manually read in all of that data. So in this example here, we are, based on the kernel version, reading in different fields within the task struct to get some information. This might not be exactly relevant to the execve example, but we have different parts of our code that look exactly like this all over Tracy's BPF code, which is a challenge because it's a lot of information to keep track of just for reading in the fields that we want, let alone when those fields get relocated to different places. So it's a challenge to not have a stable API in Linux for reading in the information that we need, which is why we're very excited about CORE. CORE is a concept that's enabled by libbpf. And in particular, the way that this works, and very oversimplified way that this works, is that libbpf provides these helper functions which read in kernel data structures for us and take into account kernel debug information, or BTF, that will let libbpf handle finding if fields have been relocated within these structs that we're reading from without any heavy lifting from us on keeping track of all these different changes. So I want to show you a quick example of what this enables for us as Tracy developers, as well as for you as a Tracy user or as somebody developing any eBPF code making use of CORE. So as the name says, we can compile once and run everywhere. So here on my development machine, which is a 5.12 kernel, I can run Tracy, have it work perfectly, reading in kernel information, and distribute that same exact file to this 4.18 kernel, and also have it work perfectly, reading in the same information, potentially from different kernel fields. And we could see that it's the same exact file. So in Tracy, we have this macro that we have defined, and under the hood, it's just essentially just calling BPF probe read, a helper function for reading from kernel memory into a variable on the stack. And if CORE is defined, we, instead of BPF probe read, are using BPF core read, which will use that BTF information to find the relocations of various kernel struct definitions. Here's it in action. So we have just this simple helper function for getting a mount namespace ID. And we're just using read kern. Under the hood, it's either using BPF probe read or hopefully BPF core read, depending on the compilation target. Another big place that CORE has changed our code base is in the include statements. So if CORE is not defined, we have to import all of the header function or header files from user API, or all the different definitions that we rely on for reading from kernel data structures. If CORE is defined, we have this vmlinux.h file and this CORE missing definitions file. And let's talk about what those two are. So vmlinux.h is very interesting. I wrote a blog post about it, so you can check that out on the Aqua blog or on my personal blog. But it's a generated file. It's generated from the vmlinux file. So vmlinux is the compiled kernel stuffed inside of an elf file. And it, based on that file, will find all of the type definitions in the compiled kernel. So this file on my system is 150,000 lines. So it has all the definitions, and it's used as a baseline for the libbpf helper functions to, essentially a baseline for you to work with in your BPF code, and for the libbpf helper functions to find the relocations. The downside to this very convenient vmlinux.h file is that it does not take into account the helper functions and the macros that you rely on in the actual header files. So I had a conversation on the mailing list about this, and to be honest, the best solution that we came up with for right now is to redefine all of the macros that we would otherwise rely on, or functions that we would otherwise rely on, And hopefully in the future, I would not expect it to stay this way, but for now we're just redefining and maintaining this header file. Perhaps the most exciting thing that CRE changes for us is distribution, and which is really what we want CRE for. So the BPF object file compilation doesn't really change much. We're just passing in a couple of variables that we need. But the place that it does change the most is in our user space Go agent. So using Go's new embed package and directive, we take that BPF object and we embed it in the Go binary. So at runtime, when Tracy starts up, it will take the BPF object out of the Go binary and load it into memory and load it into the BPF VM and not have to worry about any external dependencies. Because if we can detect that the kernel is running with BTF enabled, then we don't have to worry about also distributing a kernel-specific BPF object. And probably more exciting than distribution is the things that have yet to come. So a lot of this is working upstream, but working upstream for a better solution to the missing definitions header file. So one of the ideas that someone came up with in that mailing list conversation is to have a clang built in for checking if a type is already defined, which would enable us to have vmlinux.h, but also enable us to import the header files that have the information that we need, like the macros or functions. This is not unique to CRE, but it would be great to have better verifier output related to these CRE header or helper functions, because we certainly ran into a lot of issues that were difficult to debug. Again, not CRE or unique to CRE is missing documentation. So there's a really good blog post that Andrei, the maintainer of libppf, has written. That's a very good guide for CRE that we certainly relied on for getting this feature into Tracy. But I'm, at the time of recording this, really working hard to contribute documentation upstream. And big shout out to my coworker Rafael Tinoco, who is working on packaging kernel BTF files for distributions that don't come with BTF support. So older versions of Debian and Ubuntu, or custom kernels that don't have BTF enabled by default. It's possible to still run the CORE binary by packaging the BTF files for those compiled kernels that you rely on, and run the CORE binary literally and everywhere. So compile once, truly run everywhere, but that's something that we're still working on. That's called BTF Hub, so keep an eye out for that. Which brings me to the end of my talk. So check me out on my personal site, grant.pizza. I've written a couple of blog posts about this exact thing recently. You can find me on Twitter and GitHub, or certainly on the eBPF Slack. My name on all those is Grant Seltzer. Thank you so much.
Thank you, Grant, and thank you to all of our wonderful speakers who told us about various things related to BPF programming. So we're going to take a short break now, go get a drink, move around a bit, and we will see you back after the break for our final keynote of the eBPF Summit. It's going to be super exciting because it's about BPF and Spectre. So we're looking forward to that with Daniel Borkman, but go and get yourself a drink and have a little relax before we come to that. Welcome back. So we are about to go into our final keynote of eBPF Summit 2021. It is delightful for me to be able to introduce kernel maintainer and eBPF expert Daniel Borkman, who's going to be sharing with us some really interesting stories about BPF and Spectre.
Hello and welcome to my talk about BPF and Spectre. With this talk, I would like to go a little bit into what transient execution attacks are and how the BPF runtime inside the Linux kernel mitigates them. Before we go into that, I would like to talk a bit about microarchitecture. So consider an instruction set like x86. Microarchitecture is basically the way a CPU implements that in hardware. One example you can see here on the right side is the Intel Core 2 architecture, and then a general flow overview on the different blocks of that CPU. And that implementation or this microarchitecture can differ between CPUs and differ between vendors. For example, vendors could have different optimization goals, consider power consumption versus performance, or there could be new technology shifts. And therefore, like the internal implementation could change while the general x86 specification is still considered or like implemented. Microarchitectural concepts, they include a few things. For example, branch prediction. Branch prediction basically predicts the outcome, but also the target of a branch before they're actually known. Out of order execution. This is basically there to avoid stalling the pipeline inside that CPU. For example, it could be stalled because of loads from main memory. And with out of order execution, you could reorder instructions to keep it populated in the meantime. And speculative execution is basically there to continue the execution with the predicted outcome. And that means, like, if the prediction is true, those executed instructions, they're allowed to be committed and to retire the CPU. If the prediction is false, everything basically has to be unrolled and re-executed with the correct outcome. And those instructions that are executed with the prediction, they're basically called transient instructions. And if a rollback happens on misspeculation, basically there are a few things that need to be restored. For example, old register states, but they are preserved in the CPU and they are properly restored. Memory writes, they are buffered and they can be discarded. However, cache modifications, they are not restored. And because of that, we can have an observable side effect. And then we can use that observable side effect as a side channel to leak data. Short primer on caches for the CPU. Caches are basically what you can see here on the right side of the picture. There's an L1, L2, and L3 cache. And they provide fast access to frequently used data for the CPU. And the closer the cache is to the actual core, the less time it requires to load this data. And this can be measured by software in particular. So it can be determined whether a data is in the cache or not. Examples for access timing of those caches. For example, in the case of the Skylake architecture, I picked it as a random example here. Accessing data from the L1 cache can be up to 4 cycles, from L2 cache up to 12, or L3 cache up to 38 cycles at minimum. And for our side channel, there's like a 1-bit signal that can be used to extract data. It is by measuring the time, how long it takes to access data. If the time delta is low, it means the data is in the cache, of course. If the time data is high, the data is not in the cache and it has to be pulled into the cache first. And this can be compared to known in-cache, not in-cache timings. So you can infer information from that. To give an example on how with BPF and how data can be leaked covertly, you basically have a leaker program, and typically if there would be no speculation, it would point to a BPF map value. Under speculation, it could point to an out-of-bound attacker-controlled address. How we do that, I will show in a few examples later. And here you would first read a byte from memory. Then you would shift that to a specific bit position to extract individual bits from it. And with the result from this index here, which is either hex 200 or hex 300, we can access a valid known BPF map. And based on the time, how long it takes to access this data in the map, you can reconstruct the information, the individual bits, whether they were 0 or 1 from that leaked value byte, whether they were in cache or not in cache. And of course, between each runs, you have to bounce the cache lines from the CPU so that you can actually reconstruct this data. And generally speaking, it's not just BPF, it was used as an example here, but any runtime is affected because those are hardware bugs. They are not triggered by any software bugs whatsoever, and the execution is actually safe without CPU speculation. Now you may wonder, well, what if you just remove this measuring of time as a means to avoid having such a side channel in the first place? Well, research has shown that such timer can be reconstructed in different ways. So this would not mitigate such attacks and would not be enough. In general, Spectre is basically about injecting misspeculation on purpose and then to covertly leak this data through a side channel. And there are different ways to trigger such misspeculation. And here in this talk, I will give a few examples and also show mitigations that we do inside BPF in the kernel. I won't be able to cover every single aspect because of the time constraints, but I will focus here on Spectre V1, V2, and V4, and later also explain a bit more on how they relate to process capabilities. In case of Spectre V1, it's called bounce check bypass. It is basically to gain out-of-bound access under speculation. And the CPU basically reduces the performance penalty by predicting the outcome of branches. What you can see here is you have an instruction stream that the CPU is processing, and here's a table where the CPU can look up based on a given index the outcome, whether a specific branch was taken or not taken. This is typically implemented in CPUs through a so-called PHT, pattern history table. And of course, this is expected to be sometimes wrong. And the index here is typically just a partial virtual address. It's not the full address. And that can lead, as one example, to so-called interference. What you can see here with the P and Q example, if they both point to the same map or like index, if they both point to the same index, they can mess with each other and then affect the CPU prediction of that. Attacks in general, they inject misspeculation for the array bound check so that they can then access data out of bounds. We have a small C example. So if array max in here, if that data is not in the CPU cache, the CPU would go and use the prediction. And if it mispredicted it, you would have an out of bounds access that you can then leak with the example I showed earlier. And one example that is more concrete to BPF here, in the yellow box, you initialize a specific stack slot to 0. Then in the red one, you load an out of bound address that was provided by a map value or inside a map value from user space. And in the violet box, you read a specific bound that you then turn into a slow loading variable by binary ANDing it with 1 and 2. So this will basically result into a known 0 constant. And then you subtract 511. So you reach the same stack address as the one before that we populated with 0. And then you check the bounds, whether the provided attacker value is the same or not compared to the bounds. And if it is a known bounds where the access would actually be valid, if there would be no speculation, then basically you can, under no speculation, you would basically read back the stack slot of 0. And if there would be a misprediction from the CPU, you could then load an arbitrary out-of-bounds address and then leak this data. How does the verifier mitigate this attack? Basically, the verifier will observe that this calculation here will resolve into a constant, and then it will rewrite this prior pointer arithmetic into a pointer arithmetic that is using a constant value so that there's nothing to speculate anymore. So it will basically eliminate speculation if it's possible by rewriting those instructions with constants. And what happens if that offset is not known? Well, if it is not known but bounded, you can still do pointer arithmetic with that, but then the verifier will safely redirect speculation to be within array bounds. And this is something that looks like here. You will ask yourself, what's that? Basically, that algorithm, I will provide a short example here. If the maximum bound is 32 and the CPU speculated a value of 31, which means the offset is within bounds, then what you can see here, it will actually result into an identity function so that the 31 can actually be added. But if there's a value 34 speculated and it's out of bounds, what will happen is the CPU will, like this whole value will be masked to 0, so that that speculation is redirected in a branchless way to be within the array bounds. So basically the steps that the verifier does in here is it observes pointer moves and then derives maximum register limits to later on generate such rewrite with the algorithm that I showed earlier. And it will also spawn a new verification path to check the program when there is such truncation of the offset to 0, so that everything is safe under this path as well. Another example which will exploit pointer type confusion under speculation here. What you can see here is like there are two mutually exclusive paths. Each of them are safe if you would execute them without speculation. But if there's misspeculation, what can happen is that there will be an attacker controlled out of bound access because like the R6 register here will be overwritten with an attacker provided one, and then we will read a byte out of it and leak it. And basically what will happen is the CPU mispredicts both of these branches to be false so that the code falls true. And this can be done through branch interference, what I showed in the earlier example. An attacker will basically attack colliding entries in the pattern history table so that those two branches are not taken. And then you can leak this data. So what the verifier will mitigate in this case here, it will verify so-called impossible paths for safety that can be reached from speculation. So it will spawn a new verification path to simulate this. And if there's such type confusion and it will lead to memory access that is invalid, it will reject the program, as you can see in this example here from the verifier. Now going to Spectre 2. Spectre 2 is basically an attack that is targeting the branch target buffer. The branch target buffer is basically there inside the CPU to reduce the performance penalty by predicting the path that branches take. So basically you have an address and on that address there's a branch instruction and the target may not always be known. So the CPU will start to guess on the target address. And that is also expected to be sometimes wrong. And the issue here is that the index into this table as well is only taking a partial virtual address, for example, the lower bits only. And an attacker here can inject misspeculation so that it will it can control the BTB and lead to a misprediction so that it jumps to an attacker-controlled code for leaking out data. How is BPF affected here? Well, everything is affected that has indirect calls. For example, There can be indirect calls inside BPF helpers. In this case, it's BPF map, different BPF map implementations. But it can also, another case that is also affected is BPF tail calls here, where you basically look up a different program that you jump to based on a map index value. I won't go into the indirect call case. I will refer you to the appendix. There are some pointers there if you're interested, but we'll look here a little bit closer into BPF tail calls and how they work internally. So think of it as execv, where you replace the current executing process with the new one. Basically, in the interpreter, we are looking up an entry from a given array map, and we fetch the new program from there, and then we start executing instructions from that program. And if you look into the just-in-time compiled code, here's like an example from x86. In the end, we have this indirect jump here, where we jump to whatever is in the address, whatever address is in the register REX, and that is subject to misspeculation. So in the mitigated case, we basically implement red pollines, also called return trampolines, to basically trap speculation in a loop. This was the original designed red pollines, this concept from Google folks, and we implemented that in the BPF JIT compiler as well. It basically, like in the yellow box here, we basically create, we modify the return stack to force a return to the new target address instead. And if there's CPU speculation, this will be captured in this pause elfence loop. Pause and elfence, both because to free up CPU resources to avoid wasting them during speculation. And there's also an optimization where we basically can remove the possibility to speculate in general. So if there's no entry inside that BPF tail call map, we fall through. That's the way BPF tail calls work. And in this case, we just emit a no-op instruction. And if there's actually a new target program in the BPF map, we will directly jump to it. So it's a direct jump in here. So direct jump versus no-op, this can be swapped out. And with that, there's nothing to speculate. This is, of course, only possible if map and keys if they are constant, like from different paths. Otherwise, we will go and emit a red polline. And we will do this optimization for privileged in particular. There's a small helper in libbpf which can be used, which is called libbpf static that we added. And it will basically emit a small assembler code, which will then guarantee that such optimization can be performed. Now going to the spectre4 case. spectre4 basically attacks the memory disambiguator, which speculates on memory dependency. So for example, consider out of order in execution on CPUs. It will predict whether a particular load depends on an earlier store. We have an example here on the left side. Those are all addresses that are not known. Do they all point to the same memory location? Well, the CPU does not always know that, and it tries to guess or predict that they do or not. And that prediction is also expected to be sometimes wrong, of course. And an attacker triggers a misspeculation such that a load can overtake an actual dependent older store. And then with such gadget code, you can then read out stale data or out of bound data and use it for leaking. Consider this example. We first store pointer A in a given memory location, and then store pointer B to the given memory location, and then load it. If there's a misspeculation on that dependency, it will reorder it. And then you first have to store again to pointer A, and then you load it. Instead of loading pointer B, what would be expected under speculative execution, you would then load pointer A. An example attack inside BPF, it's basically about creating fast versus slow registers. So on a given stack slot, you first store an out of bound address, and then you train and then you copy the R10 register, which is the stack pointer, over to R9, and then you train the memory disambiguator to break the R9, R10 dependency link. Then you prepare the program to call into BPF ring buff output, a specific helper function in this case. And later on to that same stack slot, we now store a valid map value pointer into the stack. And right next to it, we read it out again, but this time through a different register, this time through R9, and then we load data from it. So what can happen here is that the memory disambiguator can misspeculate this R10 or 9 dependency, and then it would go and execute that load ahead of the store, and therefore load under speculative execution this out of bound address and leak data this way. Consider like that, without any CPU speculation, we would read out that valid map value pointer again. So where do we actually speculate here? The speculation happens because of the call to the BPF ring buff output code. Internally, the R10 register is being pushed and popped to the stack because of the calling convention, and register R9 stays in the CPU. So this will be in a CPU hardware register. So this will be a low latency register, and R10 is not yet known. Therefore, the CPU starts to speculate. How's the BPF verifier mitigating this? Well, it will observe pointers spill and fill to BPF stack. This can, for example, happen when LVM compiled programs run under memory pressure, or it will also observe first use of BPF stack slots through data or pointers, and then it will insert a so-called no-spec BPF instructions, which then the JIT backends like x86 translate to LFENCE instructions, which then avoid this overtaking. And with that, it will be mitigated. How does this relate to process capabilities? Under privileged BPF, which is, for example, used in tracing, where you can actually read kernel memory because you need to walk kernel data structures. Those programs, they basically have the Spectre v2 mitigation enabled as with the rest of the kernel, and the performance impact can be reduced because of the red Pauline avoidance. And in general, there's rather little practical impact for the vast majority of the bigger BPF projects. Unprivileged BPF, if it is enabled, it will have all the mitigations transparently enforced, and the performance impact can be low to medium depending on how or where the V2 and V4 mitigations are applied. So in short, the BPF runtime transparently applies all the spectrum mitigations, and some of those even harden the code also for non-spectral attacks. They are enforced on top of the mitigations that are also done by the rest of the kernel. And the BPF verifier partially performs deeper static analysis than compilers because it also spawns path analysis under speculative execution. The verifier tries to eliminate speculation possibilities where possible, and it applies the mitigations for the V4, which are more expensive only when necessary. Yeah, and with that, I would like to conclude my talk, and I would like to in particular thank Jan, Piotr, Benedict, and Adam. Those are like security researchers who helped and worked with us to improve BPF for the mitigations, and also John for bouncing off and Alexei mitigation ideas. And yeah, with that, I would like to open up for questions. Thanks a lot.
Thank you for that, Daniel. I particularly appreciated a really clear explanation of what Spectre is. So that was fantastic. So we got lots of questions came in. The first one was really about performance. You said that the verifier is creating these instructions that will mitigate attacks. What's the performance cost of those instructions, and can you avoid adding them?
Yeah, so actually for the Spectre v1 case, in the normal use where you have pointer arithmetic, you might use constants most of the time. And with the mitigation should actually be slightly faster, because the verifier rewrites this in a constant with a register that uses a constant. For the case where you have the masking, it's slightly slower, but it's still branchless. For the case where you have red booleans, you can avoid it in your application code, and then it will create a direct jump, at least for the privileged applications. And for the spectral before mitigation, where we use elephants, there you might have a small performance hit because you would stop speculation in that case. And that's for the first use of the stack slot or under register pressure, but the latter can potentially be avoided.
Brilliant. So our next question is about the implementations being baked into the just-in-time implementation. So was there any consideration of actually baking them into the bytecode itself, perhaps by teaching LLVM about the mitigations?
Yeah, it's an excellent question. So basically, teaching LLVM about it would not necessarily work, because attackers could write BPF instructions by hand manually without using LLVM and then load it into the kernel. So we need to prepare for that as well. And not all of them are in the JIT. So for example, like the Spectre V1 and V4 mitigation that we have is baked into the BPF verifier. So we actually do this mitigation with BPF instructions rather than with the JIT. With the JIT, you only have the red boolean case where it's really needed there, because you cannot express this with BPF.
All right. And then we also got a question from Nate about why do privileged BPF programs include the V2 mitigation? Could an unprivileged user use a privileged eBPF program to gain the information?
So the V2 case is basically attacking the branch target buffer, the BTB in the CPU, and that where you would create collisions in these entries there to predict the path of the, or like the target of the next instruction that where the branch would jump to. And that collision, that this can be created across security boundaries. For example, a user space kernel or hypervisor guest. So you do need to have these mitigations enabled, and also from the kernel side, in general, it's compiled with red boolean, so it's in line with that as well.
Well, I think that's all the questions we've got time for now. I can see there are quite a few more that came into Slack, so I'm sure you'll be able to answer them in there. And I really appreciate you sharing your expertise with us today. Thank you, Daniel. Let's have a giant emoji round of applause. And back to Duffy. Thank you.
Hey everyone, now we're into the last bit of our lightning talks, again with being presented by other experts. I could definitely consider Daniel Borkman an expert in eBPF. I look forward to spending more time working with him at Isovalent. Our first talk will be running and orchestrating multiple XDP and TC programs with Brian Merrill from Walmart.
Hi everyone, I am Brian Merrill. Thanks for coming to my talk today. I have very little time to cover everything that I want to cover, so I'm going to go very quickly through these slides. I recommend that if you're interested in more information, you can go back through these slides and pause them and look at them in more detail. And then there's also some links at the end of the slides for other videos and code repos to get more information. I am at BG Merrill on social media. Feel free to reach out to me after watching this if you have any questions. I'm a software engineer working on eBPF solutions and open source at Walmart. We are hiring if that's something that sounds interesting to you. So very quickly, what are XDP and TC? Essentially, they're both parts of the Linux networking stack. XDP is relatively low level and higher performance. TC is relatively higher level and more expensive performance-wise, but you have a little bit more context because you're higher up in the stack. So the problem that we have at Walmart is we want to run sequences of eBPF programs in both XDP and then another sequence of different programs in TC. So the solution that we have for this is named Leaf. Specifically, LeafD is a daemon that we have that's written in Go that does this chaining for us. this project, I'm not going to talk a lot about this project because it's not quite open source, but that is something we are working on. Facebook and Cloudflare have similar approaches, but as you can see here, it can be kind of complex to chain these programs together. So essentially what happens is you have a subsequent BPF programs in the chain write their program FD to a shared map where a previous BPF program reads from, and so it knows what program to call next. So this can be quite complex, and also has a downside that all of these BPF kernel programs essentially have to know that they're part of a chain because they have to have this logic to do the BPF tail call, which ideally is something that we'd like to avoid. So there is a relatively new solution for this. Starting in Linux 5.10, you're able to use a libxdb dispatcher, which simplifies a lot of the chaining logic. Here's kind of an overview of the XTB dispatcher and some of its details, but essentially there's a library that's provided to you or even a front-end application that allows you to do this chaining and show you the status of the chain, and you can add and remove and atomically replace these chains in a relatively straightforward matter. The XTB dispatcher uses the XTB lib, and since we use leafd, which is written in Go, our plan is to create a Go XTP lib implementation, which I have started, but it's very, very early, mostly just cobbled together ideas and quick proof of concept right now. So I'll do a quick demo of using the XTP dispatcher. So here on the left screen, you can see that there are no XTB programs loaded. If I wanted to load one, I could run the XTP loader and tell it to run to load the XTP pass program, and then I can see, if I run XTP loader status again, I can see now that on that interface there is an XTP program. Just to kind of show off a little bit the proof of concept that we have in Go, I can run the status, and I can also see that program has been loaded. But hopping back over to the main XTP loader program, I can add more and more of these in a chain. I can see a status. So if you wanted to run, these are all the same programs, but you could run separate programs. And then you can quickly see them, reorder them, do things like that. So yeah, that's how that works. A quick demo. Working on the Go implementation of libxdp. TC chaining we won't have time to get into, but there's some quick information right here about it. My time is up, and so I will end this this video. Thanks. And here's the references.
Thank you, Brian. And if you have any questions or comments for Brian on that topic, just jump into the Slack, and he is already there. The next person we have up is Simar Singh from Aqua Security, who will be talking about why is my eBPF code slow.
Hi all. I'm going to be talking about how you can benchmark your eBPF programs using various techniques. So I'm Simar. I work at Aqua Security, and I work on the open source team. I like graphs and numbers. We're going to be talking about those today in this presentation. And I also like to grow plants. So we've all been here. We've had our colleague run to us and tell us that, oh, this code is not performing, or it's too slow, or we need to improve it, or can you make this better? And just by looking at this, if I had to ask you, what do you think is taking 98% of the CPU usage? You'd probably guess one of those two. Maybe it's doing a lot of work, or maybe it's waiting on something. And you'll also be right, in fact, perfectly right, if you were to say that you have no idea what's going on. And that's what we can answer or hope to answer by the end of this presentation. So the usual benchmarking steps that we undertake when we establish a baseline for our code is we see what matters today. What are we looking to improve? And then we ship those small improvements, and ultimately keeping that in mind that nothing's ever going to be perfect. You're always going to have to pay a penalty for something. Nothing comes for free. So if you take a look at the stack of an example code base that uses eBPF, you have a Go program, could be any other language, that essentially loads a BPF program written in C, compiles it, loads it into the kernel, and then communicates to and from with that program that's running in the kernel and relays back the user with important stats. So let's focus on the top first. Let's say we want to establish a baseline. Top 3 items or 3 levels that you can structure this is black box, full program, or functional. So if you talk about black box, it's essentially looking into your program as a black box, treating it as one, and looking at raw CPU numbers. So measuring from the outside in. There are some pros and cons. It's easy to set up. It could be hard to pinpoint what the actual problem is. Then we could go a level deeper with full program profiling, which could be run within the program or within the system in this case, and that could tell us more important information, like maybe this program is consuming too much of one function call as when it runs. This is pretty simple to do with something like Go. The other aspect could be to write Go benchmarks, which could be classified as functional profiling. And that could be writing a benchmark on itself. Could be treated as a small unit of work, but it could be hard to determine what the actual cause or where the problem lies if it's outside the system. What about the kernel itself? What happens to that? What happens to that when you're talking about it? So we can take a look at eBPF, where we can seek refuge and ask an eBPF program to tell us what exactly is happening with our code. So this is an example of off CPU time, where we can ask what essentially happens when the CPU is scheduled for a program schedule to run on a CPU. As you can see, we have a lot of waiting in this program, and essentially a lot of time is wasted doing nothing. So going back to the question, this would kind of look like this. So 20% or so is actual work, and the rest is just waiting. Can we go even lower than that? What about the actual hardware itself? Yes, and that's possible if you visit our old friend Perf, which dates all the way back to 2009 and can use performance counters that are supported by certain class of hardware. And that would look something like this, where you can actually see the actual IPC count, or how many instructions per cycle were run for a particular program. In this case, you can see it's quite low, it's less than 1, so a lot of the time was wasted doing not actual work. So to wrap things up, this is how it would look like to benchmark eBPF program. Thanks.
Thank you, Samar. That was some great insight into optimizing BPF code. Our next conversation will be contextual concurrency control with Sujin Park from Georgia Tech.
Hi, everyone. I'm Sujin Park, and today I'm going to talk contextual concurrency control, a new way to use eBPF to change logs on the fly. With the introduction of multi-core machines, the parallelism and concurrency are the key for designing today's applications, and they rely on synchronization mechanisms to share resources across parallel access. Logs can be found in almost any software we can think of, and they're the basic building blocks for designing concurrent and parallel applications. However, it's difficult to configure underlying logs for applications or hardware. A variety of applications are evolving quickly, and their workloads and requirements differ from one another. At the same time, hardware is also changing very fast. In contrast, log algorithms are statically compiled in the kernel. It remains constant regardless of application or hardware change, and its update is very slow. For example, MCS log design proposed 1991 still remains in the kernel. This lack of configurability of logs make it impossible to change log algorithm dynamically and limits the performance and scalability of applications and hardware. For example, when application workload change from read-intensive to write-intensive one, underlying log algorithm might need to also change for the better throughput. Similarly, depending on application's different goals, such as throughput, latency, or fairness, log algorithm should be changed. For the example of hardware, Apple's M1 chip has 4 high-performance cores and 4 slower cores in one processor. And for better performance, developers may want to give faster cores more opportunities to grab logs. So here this question comes. Can we tune log on the fly? In this talk, I introduce contextual concurrency control, a new paradigm to tune synchronization mechanism on the fly from the user space. As you might expect, eBPF matched well to realize our goal. First, we add a new eBPF program type to configure kernel log, then change verifier and specify helper functions to support this new program type. In addition, kernel logs are also extended to expose APIs, which executes users' eBPF program to decide log behavior. With this change, we are opening a new use case of eBPF, changing kernel logs on the fly. Here's one of the simplest examples. User creates an eBPF program named custom compare function, and similar to the comparison function of qsort, it decides the order to acquire a log. If this function returns true, it moves the current node forward. Otherwise, when it returns false, the node just stays in its position in the queue. On this example, user creates an eBPF program to group waiters running on the same NUMA socket. It can be simply implemented by comparing socket ID of the first node and later nodes. Thanks to the eBPF verifier, we can limit the memory access of user programs so that log instance can't be changed arbitrarily and user can only access pre-load information. In addition, log policy program can only use predefined helper functions. For example, helper functions that returns current time or processor ID can be used inside the log policy program to decide the ordering. As with the nature of eBPF, users' log policy programs can't have unbounded loops, so we can guarantee log policy program does not hang inside. In addition to this comparison function, Concord has several more APIs that allow users to change the locking algorithm. In summary, in this talk, we saw that changing kernel log is difficult and why we need it. As a solution, I suggest to use eBPF to change underlying logs on the fly. Thank you very much.
Thank you, Sujin. And if you have questions or comments for Sujin, put them in the Slack. And thank you for that incredible presentation. Our next talk is going to be enabling user space C-native testing of eBPF programs by Xinhuan Zheng from Google.
Hello, everyone. My name is Xiwen Zhang. I work as a software engineering intern at Google. Today, I'm going to talk about our framework, mockBPF, which enables user space C-native mock testing of eBPF programs. This talk will include the current challenges, an overview of mockBPF with an example, the features of mockBPF, and the future work. By far, testing eBPF programs mostly relies on a kernel-based approach. We need to first compile the eBPF program to BPF bytecode, then load it into the kernel via BPF loader. To test this eBPF program, we also need a test program, which calls BPF ProgTest API. Then the BPF ProgTest API will call the provided eBPF program inside the kernel via file descriptor. It is both time and resource consuming. For example, at Google, testing a simple eBPF program with a special virtual machine takes several minutes each time, and most of the time is spent on VM spin-up and script initialization. This process slows down the iteration speed, resulting in poor development velocity. Additionally, the kernel brings another problem of flexibility. For example, there are kernel-specific features, and we need to know which kernel version the particular changes went in. And we can perform only E2E tests with the kernel, which could make the preparation very complicated. For example, we had to set up the socket state before testing socket programs, and there's no way to unit test specific routines unless they are exported as programs. Considering that eBPF programs are in sense C programs, we propose to leverage existing C native mock testing infrastructure to dramatically improve eBPF testing experience and enhance productivity. Instead of loading the program into the kernel, we utilize C mock testing framework to generate mock interfaces for both kernel-based helper functions and user functions, and create a test program which sets up mock expectations and invoke eBPF programs. By compiling them into 3 object files, then linking them into an x86 binary output, which can be executed in the user space, kernel helper symbols are resolved to mock library implementation, and eBPF programs can be easily and conveniently unit tested as normal C programs within microseconds independent from the kernel. Here is an example. Say we want to test the eBPF program on the left. It calls 3 helper functions. Accordingly, we create a test program which sets the expectations of the helper functions and calls the eBPF program. It is able to catch an assertion failure when you run a test if there is something wrong with the eBPF program. Then I'm going to briefly introduce the features of mock BPF. First, the mocking process is totally automated since all the dependencies stay in a container. All we need to do is to run a single line of command. Mock BPF supports multiple expect types powered by C mock testing framework. We have the control to choose different expect types like expect, ignore, and callback up to different scenarios. You may be curious about whether we can handle tail calls with mock BPF. The answer is yes. The way we handle tail calls is by stubbing a callback because tail calls are achieved by tail call helper function. And will call the callback whenever the tail call helper function is encountered. We also provide a library to support user space map emulation. Since eBPF maps are maintained by the kernel, we do not actually know if the map operations are done successfully or not if not testing in the kernel. Considering that eBPF maps are actually hash maps, we can create a user space hash map and emulate the eBPF map operations in the user space by callbacks whenever the real map operations are called. Actually, there is a limitation to do mock testing. It is difficult to perform E2E tests because we have to handle all the helper functions even if the program to be tested is very complex. To address this problem, we are planning to implement a fake model which can be used interchangeably with the mock kernel helpers to provide flexibility when one desires to test eBPF programs at different abstraction levels. It includes a set of data structures and helper functions of their kernel space counterparts in eBPF testing. The user space map emulation we talked about earlier is actually a part of this fake model. With mock BPF, testing eBPF programs could be much more convenient and efficient than ever before. We believe this framework will improve the development efficiency and benefit the community. Thank you for listening, and I'm happy to answer any questions you may have in the Slack channel.
So that was already the last talk of eBPF Summit 2021. Time is flying. What an amazing set of talks you have heard today. What do you think, Duffy and Liz?
I've learned a ton these last 2 days, and I'm looking forward to exploring some of these things live on Echo Office Hours. I think it'll be a lot of fun.
Absolutely. There's been some amazing content, and I think we've also had a lot of fun. Thank you so much to everyone who joined in, sent us some pictures of bees. My bee biscuit is very diminished now. I'll finish that off. We are going to be publishing all of the videos on this eBPF and Cilium community YouTube channel. So if you subscribe to the channel now, you will know when we've published all the videos. It really won't be long. Hopefully we'll get them up this week. We will, of course, also be publishing the slide decks, and we will let you know through Slack when they're ready. They'll be on the eBPF.io website.
This Friday, again, if you subscribe, you're going to get notified of Echo Office Hours, where we will do the final challenge of the Capture the Flag. This will be challenge number 3, and it'll be live solved by the team that you saw solving them over the last 2 days. That'll be at 6 a.m. Pacific on Friday. Definitely tune in and check it out.
And if you're in the cloud native world, there's, I guess, a pretty good chance that you might be going to KubeCon, either online or perhaps in person in Los Angeles. And if you're there, we'll be hosting the Cloud Native eBPF Day, and we'll post the links for that. So we hope we'll see you there.
Before we sign off, we have to thank a lot of people. Without them, this event would never have been possible. First of all the speakers. You did amazing. Your content was awesome. Give all of the speakers a big round of applause. Of course, also our host, Les and Duffy. Yes, let's give them a round of applause. Of course, also our host, Les and Duffy. Applause as well. The AV crew helped us put everything together with amazing transitions. You must have loved the dancing bees and all of the live animations. Also, a shout out to the CTF crew, including CTF host Tabitha Sable. I think it was awesome to watch. I hope many of you got the chance to solve the CTF challenges yourself. I hope everybody enjoyed it. Please give us feedback in the forum, and we might come back with it next year. Then thank you to all the iSurveillance folks that have helped in the back. Lots of things, little tasks have been done in the background. Thank you to all of you. Without you, this would have not been possible. And finally, thank you to all of you who have attended. You have been an amazing conference community. eBPF in general has a great community. Let's keep it that way and innovate together. eBPF has a bright and great future ahead. If this has been your first time learning about eBPF and you want to get involved, head over to eBPF.io. Good starting point to get involved into the eBPF community. With that, it is time to say goodbye, and we hope to see all of you again next year. Bye.
Thank you, everyone.
Bye, everyone.
See you next year.